It has been a couple of months now since the first KiCad and STM32 tutorial video, which discussed how to make a bare-bones STM32 PCB. Firstly, thank you very much for the attention that it received. Definitely so much more than I ever expected. I've decided to remake the video with a slightly different design to show JLCPCB assembly results, include some more tips, for example USB routing, buck converter layout and more, and also to improve the audio quality. This will be a rather long video, so as always, timestamps are in the description to help you find what you are looking for. These are some of my PCBs that all have been manufactured and assembled by JLCPCB. They all use some form of STM32 microcontroller, from low-power STM32L4s to the highest power STM32H7s and anything in between. Hopefully with the help of this video, you'll be able to incorporate STM32 microcontrollers into your own electronics projects, and know how to order the PCBs at JLCPCB with assembly. Okay, so we're going to be using JLCPCB for manufacturing assembly, as I said, and we'll go through the whole ordering process later in the video once we've finished the PCB. But first of all, I'm going to use their SMT parts library, so the parts they can actually assemble, so we can see what parts we want on the board, what parts we can actually get on the board. Now there are basic and extended parts of JLCPCB. Basic parts, essentially, you can use effectively an infinite amount of parts on there, as much as will fit on the board, and you don't pay a surcharge. Now extended parts, there'll be about 2 to 3 euros extra per part, and you can only use up to 10 extended parts. So we're going to try and use basically the majority just basic parts and only extended parts if we have to. So as in the first video, I'll be using this STM32 F405 RGT6, which is a pretty common 64-pin STM32 running at about 168 MHz. I've got the datasheet here, which you might need later. And it's always good just to browse through that, have a look what this chip can do if it meets your requirements. And I've used this chip many times. It's great because it has onboard USB, it's pretty fast, it's got enough flash and RAM. Okay, what we'll also be using to power the board is actually a buck regulator. So instead of just using a simple low dropout linear regulator, which is kind of power inefficient, we're going to be using this MP2359 switching regulator. Now, this isn't recommended for new designs if you go to the manufacturer's website, but it's a really common part on JLCPCB, and I thought for these kind of really simple PCBs, there's no harm in using this. For something you use in production, you probably don't want to go for something that's not recommended for new designs, but for our purposes here, this is more than fine. It's really easy to set up, it works with a variety of different components around it, and the datasheet, which is over here, tells you all you need to know about the application circuit, so that's really useful. Okay, so basically in STM32, we're going to have a buck regulator, and what's new in this video, we're actually going to be using USB as well. So for USB, we're going to be using some ESD protection, and this is pretty much our only extended part. So we're using this really common USB LC6 chip, which is an ESD protection chip. Okay, with that being said, we can pretty much get started. One thing I'd recommend you do is either download what is called STM32 Cube IDE, where you can set up the pins and peripherals of an STM32 chip, and this also lets you program the device. I also still have this STM32 CubeMX installed, which I'll just start right now. And this I always use just to see which pins and peripherals I'd like to use for my STM32 microcontroller. So I can click on Access MCU Selector and just wait for that to load. And then we can type in what part we're looking for. And we're looking for an F405RG. And you can see it's right here. It tells us about the package, the flash and RAM size, and so on. Double click and that'll load that into the program. And this is what I typically start with, just to see, okay, what's the layout of this device, what peripherals and what connectors do I need to make available. The first thing I always do is go to System Call, Sys, and enable the debug. So I'm going to be using Serial Wire Debug, SWD for short, but I'm going to use it with this SWO pin enabled. So you pretty much only need this SWDIO and the SW clock. But I'd like to include the SWO pin because this means I can have some sort of trace output. I can do a printf via the debugger, which I'll be connecting to this. What we're also going to be doing is actually using USB in combination with the BOOT0 switch to actually make sure we can use, for example, USB DFU, so device firmware upgrade. Okay, this is just going to be a really, really simple board with just a couple of peripherals enabled. Nothing too crazy, and essentially you can decide for yourself if you want to expand this board or build on this board, of course. This is just to show how you can link up an STM32, really basically to get this thing running. What we also want is a crystal oscillator. Now, the STM32 has internal crystal oscillators, but it's not something you really want to use. For example, if you want to use UART or something which requires precise timing, you would like to use an external crystal or ceramic oscillator. And we're going to be using the high-speed external one here. So, for example, a 16 MHz crystal. If you want to use the low-speed external oscillator, this one here, that's used for the real-time clock. But so far, I haven't really found use of that. So, basically just the high-speed external crystal. Okay, so we've got the main things there. This is pretty much all we need if we don't want to connect anything to this device. It's the serial wire debug pins, and it's the crystal oscillator. Other than that, of course, we wanted USB as well, and that's under connectivity. So let's click on here, and there's an internal full-speed USB physical layer, and that's up to 12 megabits per second. Now, this chip doesn't include a high-speed one, which is up to 480 megabits per second, I believe. You would have to connect some external IC to that. But we just really want this for debugging purposes. So click on USB OTG FS, so on the go full speed, and click on device only. And you see it'll enable these two pins, PA11 and PA12. This is the differential USB pair. And effectively USB, in most cases, you don't need anything like EV bus or an ID pin or something like that. If it's just a really simple device, these are all the pins you need. Another nice thing, just on a side note, if you go on middleware and USB device, you can actually, USB device, class for FS, you can actually choose a class. So STM32 actually delivers some sort of libraries which you can then use really quickly to actually program the device. So it could be anything as an audio device, if you want to stream audio back to the computer or from the computer, mass storage and so on. What I typically use is the communication device class. So this will then appear as a virtual COM port. So no need for any USB to UART converters. So this is of course not necessary here, just something I thought I'd show you. All right. What we might want to connect to this chip is I2C. So let's just see, if you click on I2C, click on I2C, it's chosen these pins up here. So PB7 and PB6. Now, there are other options which you can see in the datasheet where maybe I2C1 is available on other pins, or you can just click on one of these pins in CubeIDE and see, for this pin, we can choose this peripheral. So you could go through and see, okay, is there another I2C maybe which is a bit better suited? Yeah, and so on. So, but this seems fine, so let's just leave that up here. So we have I2C, and we might want a UART, for example. So let's just click on one of the UARTs. You want an asynchronous, which is the most common type, and let's put it over here. Now, I don't really like it over here because it's right next to the USB, it's right next to everything else, and we've got so much space still on this chip, so let's put that somewhere else. So I'm just going to, rather unelegantly, just have a look through here if there's any other UART. And you see there's UART 3 over here. There's no real difference, I believe, between UART 3 and UART 1 for the purposes I want. So I'm just going to put UART 3 over here. I'm going to get rid of UART 1 again because it's too close to other pins. And I'm going to enable UART 3. Yeah, so that's pretty much it, right? We've got the serial wire debug, we've got the crystal oscillator, the high-speed external one, we've got the USB differential pair, I2C, and UART, and we've kind of spread things out on this chip, and this is really useful. This is why I use this CubeMX. It's just to see initially, before I even get started with KiCad, that just the pin assignments and where I want these pins to be, and also thinking ahead to layout already. Okay, with that being said, we can actually open KiCad. I already have it open here, and create a new project. So create new project. Let me just navigate through to here. Okay. Okay, so I've created a new project in KiCad. Just file, new project, given it a name, and it's created a directory for me. So I've just called it the STM32F4 revision 2, right? This is following on from the first video. So first thing to do is, of course, we need to make our schematic. So click on Schematic Layout Editor. This will open this window here. First thing you can do is up here on the left is Edit Page Settings. And here you can choose the size of your schematic page, the orientation, and so on. What I like to do is just do an issue date. So click on this button to transfer this date to here. Revision, well, this is pretty much the second revision, so let's just call it V2.0 or just 2.0. Title, we can just fill in here, STM32. Let's just call it a test board. And the company, I'm just going to put my YouTube channel name. You can click OK, and you can see at the bottom right here, it's filled in everything for us. And that's typically a good thing to do, just to make sure you know when you made this schematic, what it's called, and so on. Especially if you have a multi-page schematic, this is really useful because you can give every schematic a different name. Okay, so what we want, of course, is our centerpiece, which is the STM32 microcontroller. So click on the top right here, place symbol, and now we can search for STM32 F405. And the nice thing is, KiCad already has this in its libraries. So we can pop that out anywhere, just left click to place it. Okay, so this is our blank chip, so to speak. We have all the power pins at the top and bottom, and all our peripheral pins left and right. So the first thing we do, I typically move things to the side. Now, remember, we have actually used, well, we're going to be using the F405 RGT6. So double click on the value field, and I'll just type in 6, just to make sure this is the pin we're using, the component we're using. I'm moving the component designator up here, just to make things a bit more neat. And we're going to divide this schematic up into sections later on as well. Okay, but let's get started with actually connecting stuff up to this device. This device is going to be running on 3.3 volts, which will be deriving from the buck regulator. So the first thing I do is place a power port, click anywhere, and I'll just look for ground. So this is our just our 0 volt reference. Sometimes the labels are placed a bit weird depending on grid settings. So press W to route wires, and I'm just connecting all the ground pins in the bottom here to ground. Now we can do something similar with the power pins up here. Click again, place power port, click somewhere, and I'm going to look for 3 volts. So 3.3 volts right here. Again, I'm just pressing M, and I can move the label because I think I changed some weird setting, which is a bit annoying. That's why the label's always a bit off. Okay, so we have a lot of power pins up here. VBAT you can use as, for example, a backup power source, as it implies a battery. But if you're not going to be using that, and we're not going to be using that here, you just tie that to 3.3 volts. So let's do that. So I move the label up here, press M to move, W to route wires, and I'm just connecting that to all the VDD pins. And you see, I'm missing out the last one here, which is the VDDA. The VDDA pin is the analog reference, and I'm actually going to give that a slightly different name. So if I look for 3.3 again, you can see there's a 3.3 VA. So I'm labeling my nets differently just to make sure I know that there is a difference. Now the VDDA pin is actually, if you look in the datasheet, that is the supply voltage for the analog part of this chip. So for example, the ADCs or the DACs. Now we're not going to be really using the ADCs or DACs for this video or for this PCB we're making. So you could just tie it to VDD. But just for the sake of completeness, because you might need this in one of your own designs, we're actually going to perform some additional filtering on VDDA just to remove some, or try to remove some of the additional power supply noise. But we'll get to that a bit later. I'll just first of all attach all the labels and nets to this device. Now, KiCad in their library have nicely arranged some of the pins on the left side here, and these are kind of special pins to this device. I typically try to not route things, but just by routing wires all across the board, because I don't think that looks very nice, and it doesn't make your schematic very readable. Instead, I use labels, or I prefer global labels. So as soon as you place a global label, and you connect that to another global label with the same name, those two nets will be connected. So click on the global label button, click anywhere, and you can give it a name. I'm just going to call it NRST. Press enter, and I connect it to here. Same with the BOOT0, and I'll tell you shortly what that actually does. We have these two VCAP pins here, and if you look on the datasheet, these are essentially for the internal regulators of this chip, and they need to be decoupled or bypassed. They need to be decoupled with 2.2 microfarad low ESR ceramic capacitors. So click on place symbol, click anywhere, and I typically look for C_small, and this is a smaller footprint if we can compare them. It's a smaller footprint to the typical capacitor, and I typically, for these kind of smaller designs, and in the schematic, I think it looks neater to just have them smaller. Okay, so click M to move again. Double click on, for example, C small to change the value. So I type in 2 mu2 to say, okay, this is a 2.2 microfarad capacitor. Again, W to route this up to the VCAP pins, and we need 1 per VCAP pin. So let me move that over here. There we go, connected. And the other side needs to connect to ground. So I can press C to copy, what I just did with the capacitor as well. So C to copy this ground symbol, and move it up here, and move it up here. Now, these have to be low ESR capacitors according to the datasheet, but I just chose pretty much the basic parts of JLCPCB, 2.2 microfarad capacitors, and these have worked absolutely fine so far. So try to go for lowest ESR, but I don't think it's too critical. At least from my point of view, I haven't had any problems yet. Now, these are pretty much the main parts we need to connect so far before we can kind of transfer stuff from CubeMX down here. One thing I want to mention is the N reset is used to do essentially a hardware reset of this whole chip. So if you pull the N reset pin low, this chip will reset. Internally, the N reset pin actually has a pull-up according to the datasheet. A fairly weak pull-up, might be about 40 kilo ohms. And that'll just make sure this chip doesn't essentially accidentally reset. But we can use this N reset pin for debugging. So sometimes the debugger will require you to connect the hardware reset pin. The BOOT0 pin essentially determines the boot mode. So if we go back to the datasheet for the STM32F4, there is a section called Bootmodes 2.213 on page 23. So you can click on the datasheet, and it'll show you how this chip can be reprogrammed and what boot modes there are. And there are additional application notes that will show you that kind of stuff. But essentially the takeaway message is, for me at least, you can pull the boot low pin either to ground or to high, and it has to be one of those. The BOOT0 pin can't be left floating. So pulling the BOOT0 pin low means the chip is essentially in a run state. So the chip will just execute the program that you've put into flash memory. If you pull the BOOT0 pin high to 3.3 volts, that essentially means that this chip is in program mode. So you can program it via UART, you can program it via USB, and so on. Now, if we're using serial wire debug or any sort of debugger, you pretty much always just want to have the BOOT0 pin pulled low, because the debugger can override and say, okay, stop the program that's running, I want to put it into debug mode. You don't have to specifically pull this BOOT0 pin high. Okay, but because we're using USB and we might want to program this thing via UART, we're actually going to make this thing effectively switchable. Okay, and we can do that by including a switch. So click on place symbol, and just look for single pole, single throw, which is SPSD for short. Actually, do we want SPDT? No, we want SPDT, sorry. Okay, so you can look for SPDT, which is a single pole double throw switch. So if you just include that here, effectively, as I said, you want to pull the BOOT0 pin low or high, and that's what the switch will be doing. So, but we also don't want to pull it directly high to 3.3 volts or directly low to ground, so we just include a series resistor. 10K is usually enough. So again, click on add symbol, and I'm just looking for R small. Essentially, again, a small resistor. Click R to rotate, and I want to double click and make that a 10 kilo ohm resistor. Again, my labels are a bit messed up, so I'm just going to move that around using M, and then I'm going to feed that into BOOT0. So on the other side, all we want to do is press C to copy, and then attach that to 3.3 volts, and the other side we want to attach to ground. Okay, and this way we can actually make the BOOT0 pin selectable between high and low. Again, either in run mode or in program via DFU mode is the main things I use that for. Now, I believe for the STM32F4, there's another boot 1 pin kind of hidden at PB2. Now, PB2 and the boot 1 pin you can use to change the boot mode yet again, but I believe you can just leave that floating. The main pin we're interested in for programming and running is the boot 0 pin. All right. Okay, so what is left to do now is to transfer everything from STM32 CubeMX. The first thing is these PH0 and PH1 is where crystal oscillator is attached to. So here we go, PH0, PH1, I attach global labels, and I will call it high-speed external in, and I will call it HSE out, so high-speed external out. Okay, now go back to CubeMX. What else do we have? What's important is PA13, which is the serial wire debug data pin. So let's call it SWDIO. Press R to rotate. Then we want SW clock, PA14. Then we want SWO, which is PB3. Now, PB3 isn't really needed. It's really nice if you want to do printf via the debugger. Okay, now we've got that. We also have USB, PA12, and PA11. So PA12 is USB D+. So we type in USB underscore D+. I'm typing plus explicitly, plus and minus later, because that'll tell KiCad that this is going to be a differential pair, and this is going to be really helpful when routing later on. Okay, USB D+, and USB D- on 11. So all I'm doing is transferring from CubeMX over here. The last things we need to do are, of course, the I2C and the UART down here. So I2C is PB6 is SCL, PB6 is over here, so that's I2C1 SCL, just to make sure later on when I'm programming this device, I know, I use I2C1, I didn't use I2C3. Okay, PB6 is I2C1 SCL, PB7 is I2C1 SDA, so the data line. And we're going to have to add pull-ups to this later on. But first of all, let's add the UART. So the UART was down here. UART TX is PB10. PB10 is UART 3 TX. And PB11 is UART 3 RX. UART 3 RX. Okay, and that's pretty much it. Now, of course, you can see I've got all of these unused pins here, and typically in a design, you'll probably use most of them anyway. What we could do is actually add just an indicator or little status LED to one of these pins. Now, you have to check the datasheet for this, but because some of these pins can't sync and source a lot of current. In general, most of these GPIOs can provide enough current to drive an LED. So let's just see what might be a good position for an LED. And I don't know, PA0, let's say, or PA2 might be a good position to connect an LED to. So let's do that. So PA2 is up here. I do just another label, and let's just call that LED underscore status. And PA2. Okay, and we'll connect that later. Now we have all of these unused pins, as I said before. Now, a lot of people say, oh, you could just tie them down to ground, but you can actually do that in software. So for STM32, a lot of the times you will have internal pull-ups or pull-downs, and that will just reduce the noise and the power consumption of the device. So we'll do that all in software. So what's left to do in KiCad is actually just do these no connect flags. So click on the connect symbol, and you can click on the individual pins. Now, once you've placed that, instead of just clicking around, click on everything, that's quite tedious, you can actually just press the insert key after you've placed one. And I'm just pressing it multiple times, the insert key on the keyboard, and that'll tell KiCad, okay, on the next position downwards, place the same symbol. Okay, so you have to do a bit of a jump here, so insert key again, and this is what I'm just going to be doing here. So for the sake of time, let me just rush through this. So all of the unused pins in KiCad, you want to just use the no connect symbol. Okay. We are pretty much done there. What we're missing now, and very importantly, are the decoupling capacitors. So this IC needs decoupling capacitors very close to the power pins, and we'll see that again in the layout and routing later on. In general, ST recommends, so let me just place another capacitor. So I could just copy, but why not do it here? So we want one bulk decoupling capacitor, which is really close to the STM32 microcontroller. Typically, I put a 4.7 microfarad capacitor. What we also then want is per VDD and per VBAT pin, we want one 100 nanofarad decoupling capacitor. So copy this, double click 100N. And we want 1, 2, 3, 4, 5. So let me just make 5 of these. Okay, and that's for this 3.3 volt line up here. So these are all the decoupling capacitors we need. I copy the power flag and I hook all of this up. So again, W to route wires and so on. Okay, bit boring, but we're getting there. Now, of course, we want the ground connected to the other side, and we do the same thing again. So these are all the decoupling capacitors. Okay, and as I said before, we also have this VDDA pin over here. Now, this VDDA pin, again, is for all the analog stuff on the chip, the ADCs, the DACs, and so on. We're not using it here, but it's good practice just to do some extra filtering on this pin as well. The way you typically do this, either a ferro bead or an inductor. So L small is a small inductor. I'm just going to pop that somewhere here. And typically you can use a fairly small value, let's say 39 nanohenries. Pop that down here, move my labels around, and we're deriving that from a 3.3 volt rail. Right? We're deriving that from the 3.3 volt rail. So connect that to the inductor. And typically I would put maybe a 1 microfarad in parallel with a 10 nanofarad decoupling capacitor. So we want 1 microfarad and parallel with a 10 nanofarad. Whoops. And other side, of course, connected to ground. Okay. And of course, we need to connect that to 3.3 volts. And in particular, the analog side. Awesome. So again, 100 nanofarads per VBAT and per VDD pin, a large decoupling capacitor, bulk decoupling capacitor of 4.7 microfarads, pretty much, and that's going to be placed close to the pin, close to the IC, sorry. We're doing a very small amount of filtering on the VDDA pin. You could do more depending how sensitive your analog application is. And that's pretty much the majority of this part done. Something we still need to do is, of course, connect some sort of crystal ceramic oscillator. Now, if we're going back to JLCPCB, we can see what parts they have available. I typically go for just a simple 16 megahertz crystal oscillator. And you can see the first one here is a basic part, and it's very, very cheap, so we don't pay a lot of money. You can see the package here. It's a 4-pin package, and that's typically what they come in. Okay, so back to KiCad. The way we can add that in, again, is click place symbol. Place symbol, and we just type in crystal. Now, there's a lot of different options here. The one we want is ground to 4. And I'll tell you why in just a second. If we go back to JLCPCB, we can always see that the datasheet is included with the part. So I'm going to open that up and go down. And as you can see here, this is actually the kind of footprint, the layout of this crystal package. You can see the actual crystal pins are 1 and 3 over here, but ground is connected at 2 and 4. And that's why in KiCad, I chose this symbol. 2 and 4 are going to connect to ground, and 1 and 3 are the actual crystal pins. Sorry. I know I'm going to be using a 16 megahertz oscillator, or crystal rather. Okay. Now, we need to connect this crystal somehow to this HSE in and HSE out. But the thing is, we also need additional circuitry around this crystal. Now, there's a really useful application note by ST. If I just Google it, just type in STM32 crystal, and it's the first result. And it's called an oscillator design guide for STM32 series MCUs and MPUs. Wait for that to load. And this is a pretty long document which tells you how you need to choose all the circuitry surrounding this crystal. So basically all this resistor and these two capacitors are what we're going to need to be adding. It'll tell you how this thing works, and so on. And it goes into huge detail how to do it. You can go through that, or you can just do a fairly simple method which works. Well, I haven't had any problems yet. First thing we need to do is add two load capacitors, they're called. And for this crystal, I know these are 12 picofarads, and I'll tell you why in a second. But let me just connect them first. So let's just satisfy OCD. Is that about the same distance? Okay. Okay. We connect those. We connect the other side of these to ground. So I'm just connecting the other side of these load capacitors to ground. Remember we said connect the crystal 2 and 4 to ground as well. That's what I'm doing here. Now, there is this thing, just to mention briefly, I connected this kind of a 4-terminal junction, and that's not something you should be doing. I'm just doing it for the sake of simplicity, because it's hard to see if, for example, this trace here is actually connected. But I know it is for this one, and you can use the electrical rules check later to see if it is connected. But typically, try to avoid these 4-terminal junctions, right? But just for the sake of time, I've just done it here. Okay, we also need a feed resistor. So click on place symbol, and a feed resistor going into here. I know that 47 ohms is a good value for these out of experience, but I'll tell you how I calculated these in just a second. But before that, let's link this up. So HSC in connects to the side which is not the side of the feed resistor, and HSC out connects to the side which is part of the feed resistor. And this is the whole crystal kind of circuit you need to connect the PH0 and PH1 pins. Okay, so let's talk about the load capacitors. The load capacitors pretty much depend on the PCB layout, it depends on the stray capacitance, and it depends on the parameters that are given in the crystal datasheet. Now, going back to the crystal datasheet, where was it? Over here. It'll tell you about the load capacitance. So for different types of this crystal, for the specific one, it'll either be 12 picofarads, 20 picofarads, or could be more. I know for the one I've chosen here, because I've looked this up, that it's actually 12 picofarads. Now, the way you then determine the load capacitance, again, all of this is detailed in this document, this STM32 application note, is you need to do, so let me just put a little text comment, so place text. The load capacitors have to be 2 times the load capacitance of the crystal, I'll just call it CLL, minus the stray capacitance of the PCB. And that's how you calculate it. The load capacitance of the crystal is 12 picofarads. And let's say, I don't know, the stray capacitance might be around 5 or 6 picofarads on the PCB. It's a hard number to estimate, but it could be anywhere from 2 picofarads, it could be up to 10 picofarads. So a number essentially in the middle is good. So we do 12 picofarads, that's the load capacitance of the crystal, minus the stray picofarads, let's say 5 or 6, and that gives us essentially 10 to 12 picofarads per capacitor that we need to put either side of this crystal. So really easy calculation. Look at the datasheet of the crystal, find the load capacitance, stray capacitance about 5-6 picofarads. Subtract that, multiply by 2, there you go. Okay, so really easy. The feed resistor isn't always needed. I like to include it just in case. And essentially all this feed resistor does is limit the drive level from this driver included in this STM32 chip, and which will then feed this crystal oscillator. If the drive level is too high, you'll essentially overdrive this crystal, meaning you'll generate additional harmonics and effectively noise and distortion. This feed resistor limits that. And the way you calculate that is, again, detailed in this document. So I really recommend you have a look through AN2867 by ST. Okay, but effectively I've done the calculation for that. And anywhere from 10 to 47 ohms for this particular crystal is fine. What you can do is effectively also just make this into a 0 ohm resistor. So effectively this is a short, but in case you need the resistor, you can replace that, the pads are there, and you can put in a different resistor to meet your needs. This is a really hard thing to do in general, this feed resistor, because it's a matter of experimentation. But I found this circuit works very well for the designs I do and for this chip. Okay, that is pretty much all we need to do for this STM32 to pretty much get it running. We'll do all the connectors and stuff shortly. Before we do that, however, let me just rearrange the schematic to maybe make it look a bit neater, right? Because now everything's just floating about and it's not very elegant. So I've moved things down here. I'm going to maybe put all the decoupling close. Boot switch on one side over here. And of course, the crystal next to it as well. So once I've done that, I can use this place graphic lines or polygons tool over here. And on the schematic, click and just, just section this off, I guess. Section this off and right click, end drawing. Okay, really crude to be honest, but something that just kind of works. Because I'm going to be reserving this part of the schematic up here for the power, and this section of the schematic over here for connectors and USB, for example. Okay, what you can do, of course, is also add text. So bottom right here, click add text, and let's just call that STM2 microcontroller. And we can just, stick that up here just to know, okay, this is that section. We have the decoupling capacitors, we have the VDDA filtering, we have the chip itself, we have these low ESR capacitors connected to VCAP, we've got everything nicely labeled, and so on. Okay, so that's pretty much all you need to get this chip up and running. Of course, you need the connectors to the debug interfaces and so on. What we can also add is this status LED. So, click on place symbol. Again, LED, small because I like the small components. R to rotate, just put it somewhere where it's convenient. And I typically indicate the color of my LEDs on the schematic. I would like, a blue LED. Now, blue LED typically has a forward voltage drop of about 3 volts. Now, I run my LEDs at a pretty low current. About 1 milliamp is typically enough for me through an LED to get it as bright as I want it to be. So effectively, we're running it off 3.3 volts, which is a supply voltage. So copy this label here because we're connecting it to the MCU. And once we drive this GPIO pin high, PA2 will be at 3.3 volts. And we're going to connect this other side via resistor to ground. So effectively, we're getting 3.3 volts here. We're getting minus 3 volts, so 3.3 volts here. And we can use 0.3 volts divided by this current limiting resistor, which we'll be putting here, to determine the actual current going through this LED. So let me link that up. Copy ground over here. So this point will be 3.3 volts. This point here will be 0.3 volts because of the forward voltage drop. Now, because I'm running it at such a low current, we're probably not going to get the full forward voltage drop across this diode, right? The forward voltage drop is when this is running at the respective forward voltage. And forward current. And that's depending on the datasheet. But typically, I put in like a 1K5 resistor. And this will get my blue LED just bright enough so it doesn't burn my eyes out, but still that I can see it. And also, we don't want to make the drive level or the drive current too high because this PA2 GPIO pin might not be able to supply the current that is actually going through this LED. Okay, so this is the pretty safe bet, is making this a 1.5K resistor. Okay, so that is pretty much all we need for this section, I believe. The next thing we need to do is actually power this board, right? And we need to connect the buck regulator to this board. Okay, so let's go back to JLCPCB. We're going to be using this MP2359 switching regulator. So this is a step-down regulator. which we're using to derive our 3.3 volt rail. So let's do that right now. I have the datasheet open here, and effectively all I'm going to be doing is following something like this circuit schematic over here. Now, it's always good to read the datasheets in full before you start the design, and that's what I've been doing. We have some sort of higher input voltage at the input pin. We need this filtering and circuitry, which is typical for buck regulators over here. We need a feedback voltage at this pin, and the feedback resistor network pretty much determines the voltage of the output. We also have an enable pin, and we need input and output, decoupling and bypass capacitors. The way you calculate all these inductor values, capacitor values, resistor values is always pretty much given in the datasheet. So the feedback voltage network is given here. So how do you calculate R1 and R2? Depending on the required output voltage is given here. How we calculate the inductor is given here. How we select output capacitors, input capacitors, all of that is given here. And I've pretty much done everything already, because I've used this chip so many times, that I'm just going to go right ahead and copy the schematic over. Now, I believe this chip, unfortunately, actually isn't part of the KiCad library. So if I just search for MP2359, and you can see it isn't, and I've actually made my own library. I'm kind of running my own global library for parts that aren't part of the KiCad library or I can't find elsewhere. And I'll show you how I made this circuit symbol. So as you can see, all I've done is made a really crappy looking symbol with all the relevant connections to this device. So you can see that corresponds effectively to this symbol over here. The way I did that, just briefly, you go up here to create, edit, and delete symbols, and that'll load the library symbol editor. You scroll down to the library you want to add your footprint library to, footprint here, and then you click on create new symbol. You do the symbol name. I'll just make it test, for example. You drag this around. What you can do then is up here, add pins to symbol. You can give it the pin name, pin number, the type, and so on. So pin name, I know, let's just do test 1, and the pin number is 1. You put it somewhere on the grid. You do that for all the pins you see in the datasheet. Then you drag a little box around it, right? You drag a little box around it, you save it in the library, and you're done, right? That's all I did. That is all I did for this little symbol over here. So really, really straightforward. There's probably much neater ways of doing it and making it look more pretty so you can get something like this. But to be honest, this is more than enough. All right, so let's start by hooking up this buck regulator over here. And again, all I'm going to be doing is following the datasheet. What I typically do to make things neat, as we did with this STM32 over here, is add labels to the pins, which makes sure I don't work in a really cramped way and I don't have to draw wires everywhere and stuff like that. So, the input pin I'm going to call buck in. The enable pin I'm going to call buck enable, and you can see where this is going. I'm just going to give everything a label. Now, this might just be my preference of doing it, but it's worked well for me so far. If you have a different preference, of course, that's entirely up to you. So you can see here, this device actually goes up to 24 volts at the input. Let's say we only want to design this for about 12 volts input, right? We want a 12 volt input as a maximum. So anything probably from 4 to 12 volts will be fine to make sure this thing turns on and can supply 3.3 volts at its output. Okay, so we have a 12 volt input voltage, let's say. So let's make another net, power net, and let's call it 12V. And that's going to be our input. What we also want to do before we feed that into the buck regulator is fuse it and also do some form of reverse polarity protection. So let's do the fuse first. So I type in fuse, and I would like to use a polyfuse, so effectively a resettable temperature-based fuse. So put that in. Current, that's something we need to calculate later on, but it's just, initially let's just say we put in a 250 milliamp fuse. It's always good to label what we're going to be using, but we need to calculate this later on. Okay, we connect the fuse to our input voltage, and we'll get this input voltage from our connector. 12 volts at the input, and then we want some form of reverse polarity protection. Now, there's a really cool video on reverse polarity protection by AfroTechMods, I think a rather large YouTube channel. You can either do it with a diode, a Schottky diode, but if you want a lower kind of power loss, you can use a P-channel MOSFET. And a P-channel MOSFET that is available at JLCPCB as a basic part is an A03401A. Let's have a look at the datasheet briefly. So datasheet says, okay, it's up to 4 amps, which is more than enough, but importantly, it has a really low RDS on. So really low drop we'll essentially get when we use this to just use as reverse polarity protection. Okay, yeah, the thing here is to note is this gate source voltage, right? So between the gate and the source, you can only have up to plus or negative 12 volts. And that'll also limit the input voltage. The way you could get away with this is, if you want a higher input voltage, is actually to connect a Zener diode with a resistor to the gate and the source. And that effectively clamps the gate source voltage. But I don't really care about that for now. And I'm only going to be running this up to 12 volts, so I can just use this transistor as it is. Luckily, if we go back to KiCad, the A03401A is part of the KiCad library. So all I need to do is select the symbol, make sure it's the right way around, and connect that as my reverse polarity protection. There we go. So we've taken it from the input, which we'll get from the connector later on. We fed it through a fuse with a value we still need to calculate. And we're using this P-channel MOSFET for reverse polarity protection. That then needs to feed. I typically use, I use a ferrite bead. So a ferrite bead, which you can find in the KiCad library here. And that will essentially act as a resistor at high frequencies. So very similar to an inductor. And if we go to JLCPCB again, if I type in bead, you can see there's 2 basic parts. And they'll have different impedances at 100 megahertz. And I typically use one which is, I don't know, 600 ohms at 600 megahertz. Let me just change the spelling here. Okay, so a ferrite bead just for some additional power supply filtering. I connect that after our reverse polarity protection. And then we need our essentially bulk input decoupling capacitor. And we're going to be using a 10 microfarad capacitor for that. And that's per the datasheet recommendations from the buck regulator. And I'll show you that in just a second again. The buck regulator datasheet recommends a 10 microfarad capacitor at the input. Okay, and then of course we want to feed that into the buck regulator, so copy my label and connect it. Alright, so we've got fusing, reverse polarity protection, and a bit of filtering. The next thing we need to look at is the enable pin. So the enable pin needs to be, I think, I believe, 0.4 volts for this buck regulator to turn on. And we can see that here. The enable input voltage is 0.4 volts. Or high voltage. No, it's 1.2, sorry. It's 1.2 volts of the input to make sure this buck regulator actually turns on. The problem is, this buck regulator, the pins, in particular the enable pin, as you can see up here, has a maximum rating of plus 6 volts. This means if we just simply connect the enable pin to the input pin, this thing's going to blow up. It's going to fry the chip. So we actually need to step the input voltage down via a simple potential divider to make sure this enable pin doesn't exceed 6 volts. So let's do that. Again, place resistors. Small resistor here. Typically I make them fairly large because then they won't draw too much current. If we put 100K and a 68K, for example, we're going to get less, quite a bit less than half the voltage at this point here. So let me just connect that to buck in, and then we take the output of that and connect that to buck enable. And effectively this means if we have 12 volts here, the voltage at the buck enable pin here will be less than 6 volts. So this thing won't fry, but it'll turn the chip on. All right, so that's something we definitely want to put there. So let's just put that next to the side here. So I could probably make this a bit neater. It looks like everything's going to be running along the top here. But for the sake of time and simplicity, this is fine. Okay, so that's everything to the left, so to speak, of this bug regulator. To the right, we have possibly the more interesting part, and this is stuff we take directly from the datasheet. What we need to do is connect some sort of boost pin over here. So boost capacitor between the boost and the switch, and the value is 10 nanofarads, so we can do that right now. So 10 nanofarads. So this is a bootstrap capacitor between boost and switch. Okay, that's that done. Then we need this circuitry around here. So this Schottky diode, an inductor, and the output capacitor. And that's coming from the switch pin. So a Schottky diode. Schottky diode, they'll give you recommendations what to use. My go-to diode, because it's available at JLCPCB, is a B5819W. As you can see, it's a basic part. We don't need to pay extra for it. And it's a SOD123 package. And just check the current and voltage capabilities as well. But I've made sure this works. So I type in D_Schottky, and you can see there's a small version here. Put that in here. I give the component name B5819W, and I hook that up. Ground on the other side. Again, this is just following the datasheet. We need an inductor. I've calculated the inductor value to be 10 microhenry. Hook that up here. And again, where's the datasheet? Follow the datasheet. There is a section in here at the bottom selected the inductor. And they recommend a 1 microhenry to 10 microhenry. It depends on the output voltage, it depends on the input voltage, it depends on the switching frequency, it depends on the load current ripple. You use that to calculate L. Really, really straightforward. I've calculated it to be 10 microhenry. Okay, we need an output capacitor. And that should be something like 22 microfarads. I am actually going to be using 2 of these 10 microfarad capacitors in parallel. This gives me lower ESR, and quite frankly, it looks cooler. Okay, and pretty much the output voltage here will then be our 3.3 volts. So I can copy the flag and just attach that here. Now, a really critical thing we're still missing is, of course, this feedback voltage here. Whatever we feed back from this output here to the feedback pin is going to determine our output voltage. Again, follow the datasheet. Setting the output voltage is done via 2 resistors, R1 and R2. Yeah, so we use our output voltage as 3.3 volts, divide that by 0.81, subtract 1, and we get our ratio of R1 to R2. Quite nicely, they've also made this table for us here for different output voltages and different values of R1 and R2. The problem is, R1 and R2 are very particular values in these, right? 49.9 and 16.2 or 9.53, values like these aren't typically standard values. Now, they are available at JLCPCB, but they'll be extended parts. And as I said before, we want to get away with using as few extended parts as possible. The way we do that is combine resistors in series and parallel. So, I've done the calculation already, but I'm going to be using R1 as just going to be a 47 kilo ohm resistor. So it's a ballpark similar to the magnitude of this R1 they give here. So we take our 3.3 volts, we feed that into a 47 kilo ohm resistor, and using this formula over here, we can calculate that actually R2, I believe, needs to be something like 15.29 kilo ohms. Again, that isn't a standard value. I believe a standard value is 15 kilo ohms, right? So a 15 kilo ohm resistor is a standard value. So we can use that. But then we just cascade that with, for example, a 270 ohm resistor, and we get very close to the 15.29 kilo ohms we need. with just using basic parts. All right, so we take the output of that. Let me just move that down a bit. We take the output of that and send that to our feedback voltage pin. All right, so I've used standard value parts to make sure I can use basic parts from JLCPCB. And pretty much the voltage here is going to be pretty much exactly 3.3 volts. So that's a way to kind of minimize the costs. Okay, so I could try and make this a bit neater over here. It doesn't look too great at the moment, right? Let me just move this around a tiny bit. Just to make sure, maybe it does look a tiny bit neater. But yeah, just for the sake of time, I'm just going to leave it like this. But effectively, everything in this top row over here is going to be to do with the buck converter. And that's pretty much it, right? We've got the fusing, reverse polarity protection, filtering, and making sure the enable pin voltage is less than 6 volts. We've got the output circuitry, we've got the feedback network, and we've got this bootstrap capacitor. And again, follow the datasheet. Everything I'm doing here is following the datasheet. Again, section this bit off, right-click and drawing. I can copy the text here, just change it. This is kind of, let's call it power circuitry. Okay, so we've sectioned off, we've got power circuitry, we've got the STM32 microcontroller over here. What is left to do is all the connectors and kind of the USB part of things, right? Okay, so we can add a connector. Now for the power connector, connectors in general, it's a huge part in itself, right? There are so many millions of connectors available that it entirely depends up to you, depends on the scenario, what connectors you need. So I'm just going to use fairly standard connectors that I might have lying around. For the power input, you might want to use something like a screw terminal. So if you type in screw into choose symbol, I'm just going to place one of these down here. I'm going to need ground from my power supply, and I'm going to use 12 volts. All right, so here's our screw terminal, 12 volts of the input, and ground of the input. And that's going to power our board effectively. Okay, what else do we need? An important part is, of course, our debug connector, so where we connect our serial wire debug to. If you just go to Google and type in SWD pin out, you can see here, this is the standard layout we want for an SWD connector. This is pretty much what all debuggers will use if you're using this 10-pin connector. And we want to follow that. We have 3.3 volts top left, we have various grounds, and here we have all the serial wire debug stuff. Okay, so all I'm going to do is transfer that over to KiCad. Again, place symbol, we want a 10-pin connector, type in con, we want 2 columns times 5 rows. Now there's different versions, counterclockwise, odd, even, row letter first. What you want is odd, even. All right. Pop that down somewhere. And now all we need to do is follow this. Okay, let me just move things around. 3.3 volts. Somewhere at the top here. And we want a lot of grounds. Let me just rename that. We want grounds all over here. There we go, and there we go. Again, no connect to make sure KiCad doesn't throw in annoying warnings. And then we connect all the serial wire debug stuff from over here. So SWDIO, proceed to copy, put it over here, and connect. Now what you could do, for safety as well, with any type of connector, is actually route this through, for example, I don't know, a 22 ohm resistor, right? This makes sure if anyone were to use this and suddenly short this side to ground, or to 3.3 volts, while this is at a different voltage, this makes sure it limits the short circuit current. And this is probably a good practice to do. For the sake of time and simplicity, I'm not going to do it. But I typically do it. Because, yeah, you don't want to accidentally fry your board or a chip. Okay. Again, back to this. Copy this over is all we need to be doing. And, okay, trace pin The next one is not connected for SWD. If you're using JTAG, you would have to connect that, but SWD is typically what I use anyway. NRST is the hardware reset pin we talked about earlier, is the bottom here. You could also, again, feed that via a low-value resistor into a capacitor to form some sort of low-pass filter network to make sure you either debounce the circuit and you avoid kind of parasitic resets. For the sake of simplicity and time, this is all you need, and this will work. Okay, again, search for the SWD pinout, use the odd-even footprint, connect it up from your SWD, from your STM32 microcontroller. And as you can see here, because I've used labels, I'm not drawing wires halfway across the schematic and making it look rough. This is the way I like to do it. If you like to do it differently, that's fine, but I think this looks a bit neater. Okay, so we've got all of this pretty much sorted. Now, the next thing is I2C and UART. One thing I forgot is actually to do the pull-ups for the I2C line. So let's do that now. Pull-ups is another topic of itself. What values do you use? The I2C specification gives recommended values. I typically use, for low voltages, 3.3 volts, especially if you're going to be using fast mode I2C at 400 kilohertz, I use 2.2 kilo ohm resistors. And that's typically a really suitable value. So all I'm doing is putting those data and clock lines high, right, via 2.2 kilo ohm resistors. If you're worried about power consumption, you can make them 4.7 kilo ohms, or if need be, 10 kilo ohms. 2.2 kilo ohms is certainly fine. Just make sure whatever you're connected to externally doesn't have additional pull-up resistors on, for example, some sort of breakout board. Okay, with that being said, we can now include additional connectors. So I'm just going to get generic connectors. We want 1 column, 4 rows. Now, I will include a 3.3 volt at the top. I will include ground at the bottom. And I will just connect the clock and data lines. And let's do the same thing for the UART. All right, we have 3.3 volts at the top. We have ground at the bottom. And we have our UART, TX, and RX. Okay. There we go. Okay, again, you could put series resistors to kind of limit the short circuit current in the I2C and UART lines as well. For the sake of simplicity, I'm not going to do it here, but probably good practice. Okay, so let's do something more interesting, and that is the USB connection. Again, click on symbol and type in USB, and you'll see a variety of different USB connectors here. My favorite USB connector is either the really chunky USB-B, the kind of, I think they call it printer connector, or you use the USB micro one. My favorite one is the USB micro one. Double click, insert it here. Unfortunately, JLCPCB does not support through-hole components yet, or any of these connectors yet. Hopefully someday in the future, but we're going to have to hand solder this. Okay, so what we need to do is connect a ground. Shield, if you're not using some sort of metallic enclosure, I typically just leave the shield floating. I don't do any some sort of business with connecting it via a resistor and a capacitor to ground or directly to ground. Leave it floating, is my suggestion. Now, opinions will vary on this, and I'm sure I'm going to get some comments saying, oh, you should do this and that. This has worked fine for me, and this is what I'm going to continue to be doing, unless I will be proven wrong. Okay. I will also be using ESD protection. So remember, at the beginning of the video, I said we will be using this part here, the USB LC6, which essentially is just a collection of TVS diodes in a really convenient package, specifically designed for USB. And it's a very good idea to do this, because USB you're going to be unplugging, plugging in many, many times, and humans will be typically doing this. Humans which are charged up with static electricity. And this static electricity will have the habit of discharging through your board, and a way of preventing any damage is using one of these chips. And luckily, that's available at JLCPCB, and I believe in KiCad, it is a standard part in the library. We don't have to make a footprint ourselves. So plonk that down somewhere here. rearrange the labels. Okay. Now we also have the option of powering this board via USB, right? If we don't want to connect anything to the screw terminal, we could use the USB power to power this board. So why don't we do that? The problem is we have two different power sources. If they're both connected at the same time and we just link them together, something's going to blow up. The way you prevent that is because we effectively already have a diode-ish thing here, we can use a Schottky diode. Actually, let me draw that on this side here. And we link that up. Effectively, this is kind of a really simple OR gate, all right? We take... Let me just move that around here. This isn't very pretty. Okay, this isn't the prettiest thing ever, but it'll do. This is an OR gate. Effectively, we have some sort of diode-ish thing here and a diode here. And depending on which voltage is higher, that'll essentially reverse bias the other diode. So when this is 12 volts, because USB will only have up to 5 volts, it'll prefer to use, so to speak, the power source connected to the screw terminal. So let's add another power flag, 5 volts, which will connect up here. And this is the 5 volts we're getting from the USB. So let's just link that up here. Right? So 5 volts will then go through this diode into this point here, which will then feed into the bug regulator, if the 12 volts aren't connected. Okay, so we can power this board via USB, which is pretty neat, I find, because you will only need one connector to do data and power. Okay, the ID pin we don't need in this case because we're just using this device as a device, not a host. What I typically tend to do is give the connector a different name than USB D- and D+. I call it USB_con D+ and USB con D-. All right, so I can distinguish between the connector side and I can distinguish between the device side. Now, this chip needs to be hooked up to 5 volts and ground. So effectively, all the spikes will be shunted back to the power supply. Then we need to connect the other terminals to the connector and to this STM32 over here. And I believe pin 1 needs to be hooked up to D-. And of course, because these are connected internally, pin 6 will be connected to the device side. And similarly for the D+ side on the other side. So I believe this is correct. We might have to flip it later, but let's see. So D+ and device side D+. So let me just move them around a tiny bit. And this, pretty much, I believe, is all we need to do for USB. So really simple. Normally you would have to have, on the D+ line, like a 1.5 kilo ohm resistor pulled up to the 3.3 volt rail. But luckily, all of that and all the matching network is actually included in the STM32 microcontroller, in this STM32 F405. There's a really useful application note for that as well. If you just Google USB, let's have a look. Getting started, no, where is it? It was on the page. Hardware and PCB guidelines, there it is. AN4879. And this will tell you which of these STM32 microcontrollers actually include pull-up resistors, series termination resistors, which ones include physical layers, and so on. So this application note is really useful. But for this F405 RGT6 chip, we actually don't need it. So this is pretty much all you need for USB. Plus we get USB power as well. Okay, so that is pretty much, I think, it for this board, for the schematic. The next thing we need to do is actually assign the labels and numbering to all of these parts. So you can either do that manually by double-clicking and saying like F1, this is Q1, this is the first ferrite bead, and so on. Or you can have KiCad do that for you by clicking Annotate Schematic Symbols. So you can sort by how you want the numbering to be done in different sheets. You can start at 100, 1,000, and so on. I find it a bit annoying because my placement is sometimes a bit off. So a lot of the times I'll actually do this manually. So let me just do that manually and yeah, let's just skip over that part. But essentially, I'm just assigning numbers in order and in section to these component values. Okay, so I've pretty much done all the annotation now. So everything kind of ordered and sectioned to make sure, yeah, I can find the components when I switch between the layout and the schematic. One thing I also forgot was that actually it's quite nice to include kind of some sort of power indicator LED to make sure, okay, you quickly, when you plug in the power supply, it's generating 3.3 volts. And just a really simple red LED with a current limiting resistor driven by the 3.3 volt rail. Now for some sort of prototype, this is absolutely fine, but of course some production thing, you don't want to waste power just by showing an indicator LED on the board, right? You would typically have that externally in some sort of casing or something like that. Okay, one thing I was starting to do is, of course, kind of label this thing here. Let's just call that connectors and USB. Okay, so this schematic could be made prettier, of course. It's very roughly sectioned for the sake of time. But we can see power section, STM32 microcontroller, connectors, and USB. Right? Really, really simple. And this is pretty much all you need to get this STM32 up and running, with a switching regulator, with USB. So, okay, the next thing we need to do, we've finished the schematic, we've annotated the schematic. The next thing you need to do is perform an ERC. So click on this little bug up here, click Run, and it'll show you some sort of warnings. And you can zoom in and then click on each of them. It'll tell you, connect to other pins not driven by any pin. Now in KiCad, you can select pins as power inputs, power outputs, bipolar inputs, stuff like that, right? And KiCad will then say, this power input is not driven by a power output. And this is what all of this stuff is then pretty much saying. These are warnings, these are not errors. And warnings in general will be showing this kind of stuff, like why is, it's got two arrows here saying, this is not driven by anything, but these are kind of power pins. You can turn these warnings off here, and that's typically what I do. I know these warnings are fine if you go through them, so I typically just delete and ignore them. But of course, always do an ERC check and make sure the warnings are ignorable warnings. And if there are errors, you definitely need to fix them. For example, it'll tell you if things aren't connected, if global nets are not connected to anything else, for example. I believe there's a way of getting rid of them using a power flag, but I typically can't be bothered. And this has worked so far for me. Okay, so do the ERC check, make sure everything's checked, your schematic looks right, check it several times before you move on to layout and routing. For the moment, I'm going to assume this is all fine. I'll check this later on. But yeah, let's move on to component selection. And the way you do that is click up here to assign footprints. It'll load all the libraries, and this is actually where we choose the sizes and dimensions of all of the components. So let's just wait for that to load. On that note, what we also need to include are actually mounting holes. And you can do that in the layout program, but I actually do it in the schematic these days. So you can click on place symbol. I mean, although it's not strictly part of the schematic, just type in mounting. You can get the mounting hole with a pad or without a pad. I typically like them with the pad, and we'll just make 4 of them. Because I typically ground my mounting holes, and that makes it really easy for like oscilloscope ground clips to clip onto them. So we just have a couple of mounting holes connected here. Again, we need to annotate, so click annotate, and it'll just do 1, 2, 3, 4. Not particularly pretty, but let's just leave them there for now. Okay, back to assigning PCB footprints. We get this huge list now of footprints we need to assign. So for all the components which are available in our schematic, we actually need to choose the sizes on the right here. And the way you would typically do that is go, for example, to JLCPCB, say you want a 12 microfarad capacitor, you see which one of them are basic parts, then you would go through and say, okay, this is an 0805, it's 10 microfarads, and it's rated up to 25 volts. So this looks pretty good. And this is how you go through, right? Some of them are only rated at 6.3 volts, so that would be no good for our input stage, which needs to be able to see up to 12 volts. So you'd go through and kind of see, okay, what are our ratings? For these power parts, right, C1 is our input capacitor, I typically like to use like 1206 size. So just double click. So all my 10 microfarads will be 1206. 10 nanofarads, I'm going to use 0603 because, again, this C3 is a part, it's highlighted. So if you go here and click on one of these components, it'll highlight it in the schematic. All the power section I want to make fairly large, right? Power section's fairly large. Even though they might not dissipate a lot of power, it's the thought, right? Power, large. Okay. 10 nanofarads, 0603. C5. So let's have a look. C5 is, okay, that's already the next section. C5 is part of the STM32 microcontroller. Again, I could go to JLCPCB and see what they have in stock as basic parts. They've got 0603, 20 to 25 volts. That's more than enough. Again, this is not part of the power section anymore, right? This is part of the STM32 microcontroller. 0603. All the 100 nanofarads, I typically make 0402, so really nice and small. And this is the smallest that JLCPCB can actually cope with. Now, the 1 microfarad is here, and that's part of the VDDA filtering. Again, I just use 0402. Now, the 2.2 microfarads is a special case because JLCPCB doesn't stock 0402 2.2 microfarad capacitors. So the smallest they have is 0603, and that's what I'm going to be using. These are the ones that were supposed to be lower ESR, if you remember back. But these, I've been using these in all of my designs, these ones the JLCPCB has here, and they've worked absolutely fine so far. The 12 picofarad capacitors here are part of the crystal. I want small ones. B5819W are those Schottky diodes, right? So that's what we use one up here, and we use one for the switching regulator. And that was a SOD 123 package, if I remember correctly. So scroll down in KiCad over here, SOD 123. I'm sure there's more elegant ways of assigning these footprints, but this is the way I do it. LEDs, I want 0603 size. The fuse, sometimes KiCad will be annoying and not show the footprints here. And that's when you have to click up here, get rid of the filters, and just scroll down manually. I think it's because it's a poly fuse, it isn't like that for some reason. But I'm going to be using a 1206 fuse. You can put that filter thing back on again. I want, basically the farad bead is pretty much an inductor. So we can use an inductor footprint. And I'm going to be using 0805. Mounting holes, that's entirely your preference. I typically go with M4 mounting holes. There's also this button up here. You can view the selected footprint. So there's these mounting holes which also have this pad, which of course we want. And I typically like the look of these pad with via ones. Whoops. Right, they have all these vias around it. I think that looks pretty cool. So I'm going to be using those. So those screw terminal. Okay, so again, screw terminals and connectors is a whole topic in its own, right? You could probably make a 1,000,000-hour video on it and still wouldn't have covered it. I like these Phoenix PT 5mm pitch ones, or these 3.5mm pitch ones. Let's go with the 3.5mm pitch ones. We don't need something that chunky. Okay, here's something more interesting. The serial wire debug connector, remember that was a 2-column 5-row connector. And the correct size for the STM32, I typically use the mini connectors. And I typically use an SMD one. So vertical SMD 1.27mm pitch is the one I use. And it's the one that fits. Okay, connectors again. These are the I2C and the UART connectors. Entirely your personal preference. What I'm going to use are these Pico blade connectors, a very small 1.25mm pitch. I really like them and I have a couple of them in stock at home. Okay, micro connectors. Again, that is entirely up to you what micro connector you use. Even if you use a USB micro connector, up to you. You could use USB A, B, C, whatever you want. I have my own library made with one of these connectors, and that's the one I'm going to use. It's got this awful part number, 1011 something something. But they're really cheap. I think they're about 20 cents each, and I have loads of them in stock. So that's the one I'm going to use. Again, I made my own footprint for that. Inductor. So, this is a power inductor. It's not your typical 10 microhenry inductor. If you type in 10 microhenry into JLCPCB, you'll see there's loads of different inductors available here. The one I'm going to be using is this Sunlord one over here. So a pretty chunky one, and this can do up to 3.2 amps. So really, really oversized. Even though it's a small inductor, the current capabilities are oversized because you don't want this thing to saturate or even come close to saturating. You can see the footprint is a 5.2 by 5.4 millimeter footprint, and I believe KiCad has that. So we scroll through. I believe it must be somewhere here. So SMD. There we go. It's not the correct model number, right? This is MWSA0503, and this is a slightly different name, but the footprint is the same. It's 5.4 by 5.2 millimeter. So that's what I'm going to use. The 39 nanohenry inductor, that's the one that feeds the VDDA filtering. So if we look back here, it's this one here. So that's going to be an 0402, I think. Let me just check JLCPCB just to make sure. 39 nanohenry. Yep, 0402. Right, this one here. Very tiny. So 0402. It's already selected the P-channel MOSFET because it was a KiCad standard part. And all that is left is pretty much all the resistors, the switch, and yeah, the buck regulator footprint and the crystal. So let's do the resistors first. Again, anything that's part of the power section, I type to make larger. So all these R1, R2, R3, R4, R5, and anything which is part of an LED circuit. Because the LED is 0603, I'm going to make the resistor 0603. So power, LED. Then a 10K was part of the boot mode select. I can use 0402. This 47 ohm resistor, remember, was part of this crystal. I wanted it as small as possible, 0402. 1.5K is the LED. Again, I'm making it a tiny bit larger at 0603. And these two K2 resistors, these two of them, are part of the pull-ups. Now, you can make those small, 0402, or you can make them slightly larger. The reason for making them slightly larger is that you might want to exchange them and experiment with the value. And it'll be harder to solder and desolder 0402s compared to 0603 or 0805. So you might want to go with the larger size for these. Will I want to? Probably not. So I'm going with 0402. Okay, so that's all the kind of passive components, these resistors and capacitors done, all the stuff up here done. Now switches as well, that is another thing in itself, right? So KiCad has some switches already available for you. I typically just go through them to see if the footprint matches something I have. So let me just put them side by side. So I can go through the footprints and see, is this something I like the look of? And I believe this is actually one I have at home. So this is a single pole dual throw switch, which we can actually use as our boot mode select switch. This is one I'll be using, this footprint. Okay. So we have our boot mode select switch. Now we have our buck regulator. Remember, for this, I actually made this little symbol. I didn't make a footprint. And the reason why is, if we search for that part again, what was it, MP2359, the reason is because it's a really common package. I don't need to make a footprint. All I need to do is make the symbol, and in KiCad, once it comes time to assigning the footprint, I get rid of this stupid filter again. Scroll down to package, and it's a SOT23 6-pin package. Right? SOT23 6-pin. And because I've done the labeling correctly, I hope, all the pin assignments will be correct. So because there's a standard package, I don't need to make the footprint. Double click. Remember, the crystal oscillator is the last thing we need to do. It's a 4-pin package. And if we go back to JLCPCB, I look for the part again. It's an SMD3225 size. Back in KiCad, 60 megahertz, I put on this filter thing again, and as you can see up here, SMD3225, 4-pin. That's the one I want. Double click, apply, save, schematic, and continue, check everything's been assigned, and click OK. And that's all there is to assigning the footprints. Alright. Now we need to generate the netlist. Once you generate the netlist, then we can move over to PCB new up here and actually start out with a layout and routing of this design. Generate netlist. Save it. And the next thing we do is then click on go to PCB new. So here we are in PCB new, and we're going to get started with the layout and routing of this PCB. First thing we need to think about when we're doing a PCB layout and routing is how many layers we're going to have available to us. In general, the more layers you have, the easier it is to route. These days, if we look at, for example, the JLCPCB website, we pretty much have the choice between 2 or 4 layers for if we want to do assembly as well. So if we're just doing just have a look at the general prices. So 100 by 100 millimeter board, 2 layers is about €2, and a 4-layer board is about €6. So you're only paying a couple euros more to get a much easier, or to have a much easier time when routing this board. That's why typically I will go with a 4-layer board with something like a microcontroller on it, because I can have a dedicated power plane, I can have a dedicated ground plane, and I can have 2 signal planes. And for €6 for these boards, you really can't complain. So that's why we are going to go with a 4-layer board. Now, of course, you can do this with a 2-layer board, and it won't be too hard. You essentially have a ground plane on the bottom and then route power with the signal layer as well. But for the sake of simplicity and cost as well is not a huge factor, as we just saw. So the first thing you need to do is when you're on PCB new is actually do kind of the design rules and stuff like that. So if you click on the top of here, we can go to board setup. On the layers tab, you can click on copper layers and just change that to 4. And then we get these internal 2 layers here. And you don't have to do this, but I tend to just indicate that these are power planes. One thing we also have to do, and that depends on the manufacturer you're going to get these manufactured at, are the design rules. So stuff like minimum track width, the via diameters, drill sizes, the minimum, and so on. Typically, I just keep the default settings from KiCad, because they suit JLCPCB pretty well. But if you want to meet them exactly, you can go on the capabilities tab over here, and then you can essentially enter everything which you find on here. So they'll tell you all about the minimum drill hole sizes and so on. And that will vary depending on the PCB manufacturer you use. Okay, so that really basic setup done. I'm just going to leave pretty much everything as it is. The only thing we've done is change the layers to 4. Click OK, and you can see we've added 2 layers over here. Great, let's keep it on 1mm for now. We're just going to roughly lay out the parts, and yeah, and then we'll get started with layout, and after that we'll do routing. So let's import the netlist, go to load netlist, choose the netlist file we just created, and it'll start to load in. Once it's loaded in, click on Update PCB, click Close, and you'll see we have all our components which you can move around here. So just put them somewhere on the PCB area here. So first of all, what I'm going to do is actually just do a really rough layout of this board. Just see how do things fit, which connectors should go where. Some things are kind of determined by the pinout of the STM32 chip over here. Once we've done that, we can kind of get a feel for the actual board size we're going to need. So let me just do that. I'm just going to keep the grid size as big as it now. This is kind of our centerpiece, is the STM32. We have, for example, this is one of the connectors, one of the PCB connectors you can see on the rat's nest. This needs to be somewhere up here. I'm using R to rotate and pressing M to move, by the way. Here is the UART stuff, so somewhere down here. This is a very rough layout to begin with. This is the kind of the serial wire debug stuff, and most of it is on the right side over here. Then we have, for example, the boot mode, and I believe that's somewhere over here, but that of course requires a resistor as well. U1, U3 is the part of the USB, so the USB ESD protection. And yeah, so here the USB pins over here, and that's why I kind of put it close here. And that also enables us to then put the USB connector kind of the rough area where it should be. Okay. The remaining components are all kind of small passives and decoupling capacitors, and of course we have the large power section as well. What we can really do is maybe move the crystal, because that's going to take up some room somewhere where the crystal pins are. What else do we have? So typically now I have 2 monitors I'm actually working on, but you can just drag these 2 windows next to each other, and every time you click on a component, KiCad will then show you that in the schematic as well. So you can actually move around by doing that, and it'll show you the relevant component. So for example, we could move all the power stuff together. So U1, if I click on something here, the fuse is over here. So I can kind of group everything together and see how things will fit. And this is typically how I get started. And if I don't have any mechanical constraints on the board size, this is typically what I'll be doing. So I'll just try to figure out the board size just by roughly layouting the components. So let me just roughly move things about. Again, this is usually we'd spend maybe a bit more time on this to make sure everything seems alright. But yeah, let's just get all the things kind of grouped together, and then we can see this will probably be a pretty small board anyway. So let's just move everything together. This is, again, just a really, really rough layout, just so we can determine the board size and where connectors and stuff like that needs to be. Oftentimes you might want to make changes. If you see that a lot of connectors are on one side of the board, you would again maybe rearrange the pinouts of the STM32. But since we used CubeMX right at the start, we kind of figured that out from the get-go. All right, so I'm just moving, again, stuff where it should be. So boot 0. Okay, all the connectors we've done this. But then we also have the mounting holes and stuff like that. Okay, we have all this feedback network for the buck regulator, which we can kind of group together. We can find them more easily later on. We have things like the power on indicator LEDs. We have this bootstrap capacitor. Have a look. Bootstrap capacitor is kind of part of that as well. We have the enable resistors, 1 and 2. Let's move that over here. Okay. And then we have a lot of these passives still left over. All right, we also have I think this is part of the LED, the status LED. So we can move that closer to the STM32, somewhere over here. And then we have a couple more passives. Let's just see. R11 is an I2C pull-up, and R10 is an I2C pull-up. Yeah. Part of the crystal, R8, so we can really kind of move that over here. Just really rough placement. We have the kind of load capacitors for the crystal, which I'm going to move over next to the crystal. This one as well. And we're kind of getting a feel for, okay, this board is going to be fairly small. We might even consider making these mounting holes like M3 or even smaller. Or maybe even getting rid of this plating completely, just so we save a bit of space, because this is going to be a very small board. I do like larger mounting holes though, because it just makes things easier to work with. So the boot mode select switch we can pretty much put over here. That might be a bit easier. And other than that, I think we basically just have a lot of passives left over, and these are mainly the decoupling and bypass capacitors for the MCU. Okay, yeah, we'll figure out the board size in just a tiny bit. What I would typically do now, and as I've kind of placed a couple of these things together, is maybe try now just work on maybe the finer placement of things, right? So we've kind of grouped a lot of things together. We can move all the decoupling capacitors over here. And yeah, so C1112 is part of the analog. Let me just find L2, that's over there as well. Okay. Yeah, so kind of get a rough feel for the layout. Next thing is, I'll make my grid maybe a tiny bit smaller. So I've used the schematic to help me lay this out a tiny bit. And now I'm actually going to start maybe putting the most important parts together. So I'm going to place all my decoupling and bypass capacitors first, specifically for the MCU, and kind of move through the crystal, and do all the most important things first. You know, something like the boot mode select switch, that's basically a DC signal. That's not entirely important where we place that at the end of the day. You want the decoupling capacitors first, maybe route the power first, do the crystal stuff first, and then do the less interesting or less irrelevant stuff first, like the connectors. Okay, another thing I like to do, a lot of people like to keep the Silkscreen on, right? R1, R2, C4, stuff like that, which is typically good practice as well. I don't like my boards like that. I like to have these things hidden on the fabrication layer. So there's this fab layer here, top and bottom, And this is typically used what you'll send to a fab house for assembly. The nice thing is JLCPCB doesn't even need this fab layer. You export another footprint position file, which I'll show you later. But the main thing is, I move all of my component designators to the fab layer. I believe there's some shortcut to do this, but I typically move a component where it needs to be, and then I delete the relevant designate as well. Right? So I basically do my crystal stuff right now, which is pretty much as important as the decoupling. So I double click, move it to the fab layer, kind of get a better position than I had before, trying to get these load capacitors for the crystal close to the crystal, right? Everything nice and tight. I've placed this crystal here in a line with this pad of the STM32 microcontroller, so I can just move the trace right in there. Okay? Yeah. Okay, so we can actually do the decoupling capacitors pretty much now. We've done the crystal really briefly. So here, for the STM32 microcontroller, we have this large, well, 4.7 microfarad decoupling capacitor, which we'll do last. The first, more important ones are the ones that go really close to the power pins, so C6 to C10. And we'll start off with VBAT at pin 1. Pin 1, we'll get this one. So pin 1 is something over here. So you want it as fairly close as you can reasonably get it to the relevant power pin. So you can see, I mean, basically this distance between that is, what is that? 0.25 millimeters. So this is really close. This is kind of what you want. You don't want to go too close in case you have to desolder stuff and it kind of gets in the way. But this, I believe, is a pretty good distance. And I'm just going to do that for the remaining decoupling capacitors. So C7 needs to go to pin 19, which is the first VDD pin. Pin 19 should be somewhere down here. And just kind of smack bang in the middle between the ground and the 3.3 volts. Sometimes you will have, for example, pin 20 and pin 17 might be connected to some peripheral. You want to prioritize pretty much the decoupling. So you want to make sure this has enough space before these signals have enough space. I'd rather use vias on the adjacent pins for some peripheral rather than for this decoupling capacitor. Okay, so let's just continue on with that. There's another one here. We also have these two capacitors down here, which are equally as important. So, C9 needs to go to pin 48, I believe, which should be up here. Again, nice and close. I'm doing all the decoupling first, doing all the crystal stuff first, all the critical sections first. And this should always be the case in any new PCB design. All right, okay. I'm getting rid of the component designators as I go. So I move the part, remove the component designator. This is already looking pretty good. I, of course, also have my analog section over here. I'm going to put my smaller capacitor closest. All right. There we go. That's one. Then I'm putting my larger decoupling capacitor, or bypass capacitor, pretty much right next to that. And then, of course, I have the inductor that is helping to filter the whole signal. So somewhere which feeds in. Of course, that's not entirely critical if that's further away from the pins. So something like that looks pretty good, right? Close, smallest one first, then the bigger one, and then this inductor. We still have C13 and C14. That's VCAP 1 and VCAP 2. Unfortunately, as we said before, these are 0603, so they're substantially larger than the 0402 sizes. So I might have to move things around a tiny bit. All right, so I'm going to make sure, I could even move my 3.3 volt decoupling capacitor over here, and this gives me enough space, right? So this is still pretty close. My 3.3 volt is still pretty close. I've just moved it out of the way a tiny bit. C14 is hopefully our last one. And the same thing I'm going to be doing here. I'm just going to move this one out of the way, and then I'll have enough space to put this one in. Okay. So this looks pretty decent for now. We, of course, still have our 4.7 microfarad capacitor. And this one, effectively, we still need to decide where you want to put all of this power section. And of course, we're going to make this much tighter, much better soon. What I typically do with this bulk decoupling capacitor, this 4.7 microfarad one, is I put it at pretty much the opposite side to the power delivery. Because in my eyes, the power delivery will be worse further away from the actual power source, and that's where I want to put my decoupling. And by the looks of things, I want to put my power section here next to, for example, one of the power sources, which is the USB connector. That's why I'm probably going to put the 3.3 volt bulk decoupling capacitor somewhere over here, close to the main microcontroller IC. Okay, and that's pretty much all there is to the decoupling side of things. Now we can look what else is important. At least for the MCU side of things, while we're here, we might as well route the other stuff, or at least lay out the other stuff, and then we'll move over to the power section. So as you can see, I'm doing this section first, then the power circuitry. You could start with the power circuitry, you could start with the STM microcontroller. But within those sections, start with the most important things first. Decoupling is something you should prioritize. Right, so I'm moving it slightly to the left. This is the BOOT0 resistor, this 10K resistor over here. Moving it slightly to the left, so I leave space for the SDA and SCL lines. I could also put this pretty much further away. This wouldn't be too bad either, because this is a low frequency signal. BOOT0, it isn't critical where this resistor is or anywhere. So actually, let's put it over here. That's not too bad. Okay, what else do we have? We have the I2C pull-ups, which will have to go somewhere up here. And we have this blue LED, which is effectively our status LED. So let's move that somewhere. So we can just put that effectively somewhere over here. Again, this is not too critical. Again, it's a low frequency signal that's going to be applied to this. And this is just the current limiting resistor, which I put next to it. What I like to do as well is use the 3D view in KiCad. So up here, if you go View and 3D Viewer, shortcut is Alt+3. And that'll bring up the 3D view. It's extended because we haven't drawn the board outline yet, but it's really good to check, just kind of visually, does this look alright? Do the decoupling capacitors look close enough? You know, we might be able to move them in a tiny bit more, but to me, this looks fairly decent. Yeah, we've got them fairly close, could move them fairly closer. And as the board progresses, we can keep using this 3D viewer just to check that everything looks fairly decent. Of course, another critical thing would be the USB, even though we are using a really low speed USB line. It's a full speed line of 12 megabits. All right, so it's not particularly fast. It's not entirely critical how you route this, but we will actually be routing this as a kind of a controlled impedance differential pair. So here's the ESD protection for that. And you want the ESD protection as pretty much closer to the connector, as close as possible to the connector, rather than as close as possible to the chip. But we'll see about that in a bit later. Basically, you want to fit this whole power section somewhere in that region as well. The connectors, we can get rid of the silk over here and move that to the fab layer. Move that maybe a tiny bit over here. And then we also have the pull-up resistors. Yeah. So, all still part of the MCU circuit. Second pull-up resistor. Again, not too critical where these pull-up resistors are. In general, it's recommended to put them closer to the actual host device rather than to the slave devices. Then again, not entirely critical at these speeds we're running at. Up to 400 kilohertz, that's not entirely fast. Okay, so by the looks of things, SWD will probably be good just to put somewhere here. That's our debug connector. You might want to put the USB slightly higher because we also have our power terminal, power connector here, which we're going to put right next to the USB. I know, so something like here maybe, along this line. I think that might be right. That's our power screw terminal. Okay. Yeah, so we might need to extend the space here a tiny bit. Right, I select everything, press M to move to the left a bit. I'm trying to make space for all this regulator stuff over here. Okay. All right, so the first thing we need to do is actually do the fusing. So I'm seeing now the fuse is actually before all of this reverse polarity protection and stuff like that. So it probably actually is better to move maybe the fuse ahead of things, right? We might want to move the fuse over here because otherwise, essentially the USB line is unfused. We could do that. We couldn't do that. It's probably a better thing to move it over here. If you want to move it over there, let me just create some more space. Let me move that here. All I have to do is click M to move. I put it over there. Just join this up. I could decrease the distance. Actually, let me do that. Let's move that down a bit as well. Okay, look, hook that up. Again, I just click annotate just to make sure. What I typically do is also just reload the netlist, regenerate the netlist. I can go back to PCB new. If you've made any changes in the schematic like we just did now, all you have to do is click this button here, update PCB from schematic, and click update PCB. And that should have changed everything. Okay, so now, the first thing we have, well, we have this diode from the USB connector, which is from the power, which we might put over here. So this is essentially our very simple power OR gate. We have the P-channel MOSFET, which is going to feed from this screw terminal as our reverse polarity protection. And then we're taking the output of that junction effectively into the fuse. So the fuse, I try to give a bit more space because you might have to, even though it's a resettable one, you might have to access this if you're not using a resettable one. So just give the fuse a bit of space. Okay, we can just move the diode around maybe a tiny bit. And just maybe pop the fuse. I mean, we could clear this out later when we do the finer adjustments. But for now, this looks all right. Okay, from the fuse, we've got a farad bead. So we essentially just to filter. And then we are starting to get into this bug regulator territory. So when I do that, I'll click on this bug regulator and move it where it probably should be. So the input is pin 5. Just trying to make sure we have enough space. Okay, so the input is pin 5. And generally with buck regulators, or any sort of power supply, you want to keep the loop area as small as possible. In essence, that means keep things tight. Make sure you're not making the areas larger than they need be. So let's see how we can do that. All right, where do we start? How about we start with the input capacitor, C1. Input is somewhere here, so we're gonna pretty much just make that follow this path here. We're going to have to move around things, so this is not fixed. This is just to get a rough idea of how we want to route things, all right? We might, yeah, because we're going to use a dedicated ground plane, I'm not too worried if I get a direct connection back to ground here, because we're going through vias most of the time anyway. Okay, we have that, and this enable circuitry here isn't too important yet. But let's have a look at where this inductor will go. And the inductor should be somewhere here. Now, we need to see what we're going to do regarding all the space. So we probably should move this down a tiny bit. So let's move that over here. We could... So I'm just moving around just to see how things might fit. Again, this is just a process of kind of guesstimating where things might be. A lot of the times, the datasheet will actually tell you how to do the layout of these things. Unfortunately, the datasheet for this MP2359 doesn't tell you the layout. So we're just going to have to do a best kind of guess, I would say. Okay. I'm just making sure things are fairly compact, fairly neat. I'm sure people can do this better, but I've used this buck regulator several times, and I've never had problems. So that's usually what I go by. If it works, and I don't see any specific problems, then that's great. All right. So, okay, we also have this boost capacitor, I remember, which is this thing here, and that can fit in somewhere between these pins. Okay. I mean, it's not the neatest thing, but it'll do for now. And then we have the second. And we're going to readjust, It's always a little bit of process with the PCB design. You're going to find, oh, I've got a bit more space here, I've got a bit more space here, I can move things around. And typically it depends, of course, on your mechanical constraints as well. It depends how much space you have in your housing, how much you can sacrifice, and so on. Here, I don't really care how big or small things will be. Ideally, the smaller the better. But here, it's not entirely relevant. This thing is switching at, I believe, about 1 to 2 megahertz, so it's a fairly high frequency switcher. Now, you might think there might be noise issues here, and there could be, of course, if you're measuring fairly sensitive analog signals in that kind of frequency range. But for us, we're not using the analog part anyway, so you're not going to have any problems with this kind of layout, even if it looks rather close at the moment. Okay, so just doing a couple fine adjustments, a little bit of fine-tuning. Again, 3D viewer, it's really useful just to see, does this look dodgy? Does this look kind of alright? To me, yeah, it's not the prettiest, but it'll do for now. Ideally, I'd like to get this whole section just a bit tighter. Could do maybe like this. But yeah. Yeah, it's maybe I'm just spending too much time on this already. Something like this will be absolutely fine, right? We've kept things fairly compact. I mean, overall, this is spanning, I don't know, a centimeter. Yeah, a centimeter and a half. Nothing too worrisome. Before I do the enable pin, let me do the feedback, because that to me is more important. So the feedback pin here, get rid of Silkscreen, and then we have the remaining parts of the feedback network. We'll do finer adjustments with a smaller grid size later on, but for now, this should be fine. Whoops. Okay, and that is pretty much it. We just have to enable things here. So these aren't too critical, right? This is just a very low frequency signal, just telling the bug regulator turn on. That's all these two resistors are doing. And that is pretty much it. We have the power LED, and we can pretty much put that wherever we please, right? We could put that any side of the board. It's entirely it's not critical at all. So we can put that somewhere up there maybe. I'm not sure. Something like that should be fine. We'll try and put the mounting holes in next, once we're happy with this layout. Maybe move this, get rid of the Silkscreen, and yeah, okay. Okay, so this is a very, very, very basic layout. What I would do now is place the mounting holes. So let's have a look. Maybe something like that. Just need to make sure the USB connector can hang off the edge a tiny bit. So maybe like this. Okay. And typically it's a good idea to space the mounting holes, of course, depending on mechanical constraint, but if you don't have any mechanical constraints, place the mounting holes a fixed number or a sensible number of millimeters apart. So let's say, what do we have here? And I'm using the space command you might see to measure distances. So I press space, and down here, these numbers will change. So I go above this, I press space, and it zeroes everything, and then I can see how far away I am. So let's say, I don't know, we could make 40 millimeters? 40 millimeters. 40 millimeters in this axis, and we'll see in kind of the x-axis what distance we want to have apart. So again, pop it over here, space, move it over where you think seems about right. You do about 45? 45, looks good. And that means our last mounting hole is pretty much fixed as well. Again, move it over. And we want 40 millimeters in this direction. Awesome. Okay. Yes. Okay. So now we can just adjust the connectors maybe a tiny bit. We'll do that in more detail soon. Gee, and then we can just pop this somewhere. We're going to move this thing around a bit, a tiny bit later. Okay. What we need to do now is draw the board outline. So even if we go to 3D Viewer now, KiCad thinks, okay, this approximately everything fits in this space. But I don't like sharp edges, so we're going to make a board outline with rounded corners. So let's do that. So click on Edge Cuts. Click on the Add Graphics Lines tool. And then just close to your connector, essentially vertically up, I will leave a bit of space. All right, I don't know. Let's say 1 millimeter space. And I'm just going to go to the next mounting hole. At the same position, exactly vertically above. Then I go to the next mounting hole, pretty much 1 millimeter away from it, click, and go down in a straight line, and next to the other one, and just click. Okay, actually that's not a straight line, is it? Let's try that again. Okay, straight down. This should be good, I think. Okay. Same thing again. Okay, so now we just have to do this last side over here, where we go up here. Make sure it's a straight line. Okay, so now we've got these 4 edges here, and why I haven't connected them because I'm going to do rounded corners. The way you do that, we stay on the Edge Cuts layer, click on Add Graphic Arc, click in the center, click on the second point, and counterclockwise is to draw just part of a circle. Start from 0, essentially. Because if I click and I go like clockwise, I start with a big circle. I want to go counterclockwise, so I don't start with a full circle. Click, second click, and then counterclockwise. And twice more. And these join up nicely. Awesome. All right. Okay. So now we can click 3D View, and we have a nice little board with rounded corners. It's fairly small. We've left ourselves quite a bit of space. We might want to put some Silkscreen and other stuff around there. We still need to move the connectors around to make them look a tiny bit better. But yeah, the rough layout for first try, this is all right, I think. Okay. So as I said, I'm just going to move these kind of pretty much towards the edges. Just before, I'm just going to make sure I line these. Again, I typically use, there's probably a better way of doing this, typically use space just to make sure it's aligned. And we're leaving a bit more space here. There we go. Okay. Now what we can do is maybe move this whole MCU section down a tiny bit more. And we can fit our boot mode select switch over there. All right, and I'll move the boot mode select resistor over here. Okay, our SWD we can move maybe a tiny bit up as well. And we, of course, have our power LED. Power LED doesn't really matter where this thing goes. I severely dislike the aligning mechanism. Some things, when you import the netlist, are on the grid and some things aren't. Not my favorite thing. Then, of course, we have the USB connector. Again, I'm always using the 3D view just to check what I'm doing. Check the layout looks fairly sensible. Of course, we've got a lot of space still left over, but, you know, as just a little showy board, this is fine. The main thing is that you know how to wire this STM32 thing up. But yeah, this looks fairly right. We can move it maybe there. Okay, I'm just going to align this ESD protection chip so the center of it is between the D+ and D- pins. That way I can make sure the lengths between the differential pairs are matched, at least on this side. So I get it fairly nice and close. Not too close, because I need to solder this connector on manually. And I want to leave myself enough space to get my hot air gun in and not desolder anything else. So this is fairly good. Remember, this ESD chip needs to be closer to the USB line than the microcontroller. Yep, okay, so we've got a power input. We've also got power here going through this diode. We've got connectors on the outside edges. We've got any switches on the outside edges. And we've got the majority of the critical parts close to the relevant ICs. And that is pretty much it for layout. So I think we can go over to routing. If we find anything wrong with a layout, we will find that in routing. So let's move over to that. So now we're ready to start with the routing. And the first thing I do with routing is go to the track sizes and add several track sizes I'm probably going to be needing. So click on Edit Predefined Sizes, and I typically go with 0.3 millimeters, and that's really useful for the LCSP package pins of this STM32 microcontroller. 0.5 and anything up to 1 millimeter I typically use for power. So these should do you fairly well. We're going to look at differential pairs later, because we're going to be needing that for the USB routing. But basically just enter these pairs to start with, and then click OK. Okay, another thing we need to do is add the power planes. Because this is a 4-layer board, I'm going to be using the inner 2 copper layers as power and ground. Specifically, the in one, so this layer here, is going to be a ground pole. So click on Add Filled Zones. Just click on the first corner up here. I'm going to choose my ground net on in one. These settings are typically fine. And click OK. Now we just go around the board. You don't have to fit it exactly to the board. KiCad will do that automatically for you. So all you have to do is click around here. And the last one. Once you've done that, you will have a ground port, which you can see over here. Right? It's connected to places with these thermal relieves where they need to be connected. You can change the spoke width of these thermal relieves by changing these values here. So we could do maybe 75 millimeters, and that makes these spokes a bit thicker. But yeah, the normal values are typically fine. But why not? Let's just go for a thicker spoke width. Okay. We also want a layer, this layer here, in 2, so the lower copper layer, just above the bottom copper layer, we want that to be a power plane, specifically 3.3 volts. We don't have to draw it again. We click on our original copper layer, press Ctrl D, and then left click, and we've got another one. So you can press E to open the properties. We change it to in 2, and we want 3.3 volts. Click OK. There we go. Now we have 2 of these layers on top of each other. Well, not on top, but on separate layers. And you can see here, the places where it should be 3.3 volts, it's filled that. And so you have a nice big chunky ground and power port. Okay, and this will make our routing life a lot easier. Because any time we need power, I know, for example, 3.3 volts, we don't have to route that all the way back to our buck regulator. All we have to do is make a really short, wide trace and drop a via into that power plane. And because it's a dedicated power plane, a dedicated ground plane, we're going to get really nice low inductance. Okay, so with that being said, let's start with routing. So I'm going to move to my front copper layer. I'm going to select my 0.3 millimeter track width. And the first things I route are the first things I did in layout as well. So specifically anything important, such as decoupling capacitors, the crystal, stuff like that. So anything high speed and critical, I will route first. So let's do that. So I'm just going to go around the board, decoupling capacitors fairly arbitrarily. Got my crystal here. Just click. Because we've done the layout, I think, fairly nicely, it makes our routing job a lot easier, right? I could just click and draw it out. I don't have to move stuff around. My routing job is a lot easier now because I just spent a bit more time during layout. Okay, all the decoupling capacitors first. We could move some of these closer, but to be honest, this is probably pretty fine as it is. All the ground and power connections, you know, like 3.3 volts, we're all going to do later with vias. So that will come fairly close to the end. For something like this, I could use thicker traces for these kind of connections. But to be honest, I've always fared pretty well with these. Okay, So that's already pretty much all the kind of really critical ones for this part. I could route the LED here. And I could maybe put a thicker track down here. Now sometimes you'll have, there's this thing called tombstoning, which happens with PCB assembly, specifically for small SMD parts, something like 0402 and the like. The tombstoning occurs if you have uneven mass distribution. So you have a larger thermal mass here and a smaller thermal mass here, for example. And that might cause one side to heat up quicker than the other, and might cause the part to kind of flick up and look like a tombstone. Truth be told, I have never ever had a problem with that. And I've done some pretty crazy mass distributions, to be honest. Like a lot of power planes and poured copper on one side and finished traces on the other side. I haven't had a problem so far. I might just be lucky, or maybe JLCPCB is just doing too good of a job. Or So I think, but just be aware of that. Be aware that you don't want to make them too uneven, the mass distributions. But something like this, where you have a thinnish trace here and a bit of a thicker trace here, absolutely fine. Okay, so I'm just going to scout around the board and see what stuff I can link up. Okay, I could connect SDL. And generally with track spacing, you see here I went up and then I went immediately right a tiny bit to give these two signals a bit more space, to avoid crosstalk, interference and all that. Generally, I know 2 to 3 times the track width is what you should be aiming for. Okay, I could change the track size to maybe a thicker trace, but this is okay. Okay, what else do we have? We've got a lot of grounds here. Of course, we've got our UART. So again, I'm going to route it out here and immediately come out. Same thing here. Give myself some good spacing between the traces. So again, I like to check in the 3D viewer several times that things look fairly decent. Okay, of course I could move these two resistors in closer. Should I do that? Maybe I should do that, yeah. Just to make it look a bit nicer. There we go. And then I can just connect them again. I just really like using the 3D viewer just for kind of a reference. We also want to route our serial wire debug. Now, serial wire debug, you might think, why didn't I route that right at the beginning? It's actually a really low-speed protocol. So only maybe, I think up to 4 megahertz or something like that. So nothing entirely critical. There we go. So just route it out. Put that in there. Now I could... Let's see. I don't want to do this. Yeah. I've got SWO as well. So I could either go through here, right? Go over here. Which I actually might do, to be honest. I could also go the other way around, but that's doesn't really matter. And then here, I'm just going to drop a via. I press the V key. And I can just kind of diglet my way over here. And I'm keeping all the trace. I try to stay as much as possible on the top layer, but I have a really short trace on the bottom layer. For 4-layer design, not too critical, but it's a very small jump, just to make sure I can follow the traces. I also have my SWO, so let's route that. And that can just fit like nicely in between this connector here. Yeah, so again, 3D viewer just to make sure things are looking all right. Looks pretty fine. We've got enough clearance between all the traces. Yeah, that things look fairly decent. Okay. We also have the N reset line, which you could do at some point as well. But I think I might save that just to the end. I kind of just want to do the power stuff first. So let's do the power stuff first. So there's 2 ways I typically do that. One is I either use really thick traces, right? I just click on a thick trace and then I start routing. Or you can actually use copper pores. So you can add filled zones. And for example, if I want to do this thing here, click once. I want it on the front copper layer and I want buck in. So I can just choose that. And then instead of routing traces, I can just route essentially as a copper pore. Right, and then press B to fill the zone. And you see it's kind of filled the whole zone for me. And if I want to make things thicker, I could say a minimum width, maybe 0.4. I don't need that much of a clearance. Things like that, right? So you can either do it via traces, or you can do it this way with filled zones. For the sake of time, let's just do it with tracks. I think it looks cooler doing it with copper pores, and there's some advantages to doing it, but as I said, for the sake of time, let's just use really chunky traces. So 0.75 millimeters. There's a thing in KiCad called the calculator in the main menu over here. If you're worried about how much current capabilities your traces have, you can just go on track width. And then you can say, oh, I've got a 0.5 millimeter track. For 20-degree temperature rise, I can carry 2.6 amps. So as you can see, a small, really thin trace can actually carry quite a substantial amount of current without heating up too much. So 0.75 millimeters for this very low power board is absolutely fine. So again, just routing. We've made our layout job easy-ish. And that means our routing becomes easy as well. So here I'm just seeing not entirely aligned. I believe you can use a shortcut like N or something to make the grid smaller, but I'm still very manual with a mouse. Okay, so just link everything up. Again, I could use wider traces here, but 0.75 millimeters is, as we saw, more than enough. If you use thicker traces, of course, for example, for something like this, I could use 1 millimeter. You will get, of course, low inductance, which is something you typically want in these kind of power circuits. So yeah, but as long as you're well within the current carrying capabilities, you will typically be safe. Okay, we still have to route this directly, and we also have this 5 volts from the USB, and this little buck thing over here. Let me just a bit finicky. Okay. So we have a lot of 3.3 volts and power not connected yet, and we'll come to that in just a bit. Remember I said we're going to do that with vias. What I'd like to do now is just connect this 5 volt thing up. So typically for USB, these kind of fine pitch things, 0.5 millimeter is pretty good. Okay. Okay, we still have this power indicator LED up here. And other than that, we've got the SSN reset signal. We could do that now. So again, switch to 0.3 millimeters. It's not a critical trace. Let's see how we want to route that. Yeah, I mean, it's not really entirely critical. So maybe, actually, let's do the USB one first. Now, USB, I said, we want to use controlled impedance differential traces. Now, you can either use the KiCad calculator again, and the calculator will tell you all you need to know about the transmission line kind of effects. So if you have a microstrip line, if you have any sort of compiler waveguide, you can calculate all that depending on your PCB parameters. Luckily for us, our life is a bit easier. We just use the JLCPCB impedance calculator. If you go over here, I would like to know the impedance and trace space. For USB, you want a 90 ohm differential impedance, 4 layers. We're using a 1.6 millimeter thick board, and it's routed on an outer layer as a differential pair. Now we have to tell JLCPCB what trace space in mils, so not millimeters, we're going to be using. I typically go for the widest given here, which is 8 mils. Okay, so for 8 mil trace space, so the spacing between the differential pairs, the recommended trace width is 10.28 mils. Awesome. And this is for the certain stack up I typically use, which is the default pretty much. So we go back to KiCad. We go back to our edit predefined sizes in the track window. Go to differential pairs, and we can type in mils directly. You don't have to type this in as millimeters. So it was 10.28 mil. The gap was 8 mil. We're not going to be using vias, but we're just going to fill in 8 mil via gap. Click OK, and we've added some differential pairs. If you want to route those differential pairs, click on Route, click on Differential Pair. Right-click, click on Select Differential Pair Dimensions. width 0.26. This is our custom one we made. All you have to do, click, and start routing, and it'll route it as a differential pair. There we go. And it'll try to kind of match the lengths and stuff like that and make sure it maintains its 8 mils of distance. But of course, when going into these ICs, you can't maintain that. Okay, now we need to route the other side of the connector. So again, just click and go. And remember, because we named them D plus and D minus like this, KiCad knows that these are differential pairs and they should be routed that way. If you go route differential pair and click something that isn't named that way, it'll say, you know, it's not named properly. So either NP or plus and minus. Okay, so that's looking all right. What else do we need to do? So basically there was the NRST thing now, so how about we do that? So NRST, I'm just gonna move right out here. Again, just a fairly short trace just to jump across. And we can, again, route it like this. Okay, we still have the BOOT0. Again, another really low speed signal. We don't really care too much how we route this. Something like that should be more than fine. Okay, not the prettiest, but it'll definitely do the job. So I think all our signal traces are pretty much routed now, unless I'm mistaken. All the power stuff has been routed. Yeah, so all we have to do now is connect all the grounds and 3.3 volts. So let's have a quick look at the 3D view again. Everything's pretty much routed, a very, very, very simple board. But now we can pretty much just route all the power and ground. So I typically stick with the normal via sizes. If you want to go larger, you can add them here. So if you want a 1mm and 0.6mm drill, you can do that. If you want to do smaller, it depends on what your manufacturer can do. Typically, for most signal traces, 0.8 and 0.4 is a good VSC size. So how about we just stick with that? So click on the little VIA button here, add vias. If you click, it'll have no net to begin with, but if you just drop it on something which has a net, it'll actually adopt that net. And what we want to do with vias is get them as close as possible, but not in the pad. You can do via in pad, but the problem is with assembly, some solder paste might get sucked through. So I try to put it as close as possible to the pad, you know, something like this, and one via pretty much next to every one of these pads. If I have a bigger capacitor like this, I might put two, you know, one here and one here, but typically one is pretty much sufficient. So now I'm just going to hunt out all the 3.3 volts, which need to be connected, which aren't through hole, and just pop them as close as possible to where they need to be. Of course, it depends on the current capabilities you need. You might need to put more down. We'll come to the power section in just a bit because that's a tiny bit more interesting. Pop one over here, and we'll then do the same thing again for all the ground stuff. So here I might want to put maybe two, because this is the VDDA pin. I might need to... Essentially, the more vias you have, and the closer the vias are spaced together, the less inductance you will have. And that's something you should definitely be aiming for. Okay. This is a tiny bit boring, so I apologize, but... Okay, and then I use thick, short traces. So I switch to 0.5mm, and I link all of these up. Right? All the 0.3... sorry, the 3.3 volts I link up. Thick, short traces, vias close to the pads, but not entirely in the pads. We'll have a look at this in the 3D view in just a second. And the nice thing is, because we have this solid ground plane, right, on the second inner layer, all of these points are got a really nice, solid ground plane. So yeah, really low inductance. Exactly what we want. Okay, now, I said we come back to the power section. The power section, I typically drop quite a boatload of vias around it, right? Minimize inductance, make sure the power handling capabilities are what we want them to be. All right, so just pop a couple around here. And then I pop some next to here as well. These large 10 microfarad capacitors. And then, of course, the feedback pin. And the feedback pin, I'll put quite a number as well. All right, we just want to make sure the inductance is as low as it can reasonably be. Again, I'm just going to use very large traces. You could use a ground pole for the sake of time. I'm just using very large traces. You can kind of link them up like this. But basically, doing with a ground pole would be much neater, right? Okay. Might just use the 0.7 millimeter trace here. Okay, and that means pretty much all the power here is nicely linked to the internal 3.3 volt copper pole. Yeah, okay. Okay. One note also regarding the crystal. In the previous video, I actually cleared out this area underneath the crystal. So you can do this by adding in, for example, a keep out area. So I would put in a keep out area here, say in one, and then keep out copper poles. So I'm just going to do it very roughly now, but you could do something like this. All right, where you just make this is very shabby, so I advise to do it a bit cleaner than I'm doing right now. Oops. So one thing also regarding the crystal is in the last video, on the first KiCad STM32 video, I also put a cutout around this area and kind of attached the ground of this crystal only at one point. Now, I've heard a lot of people did not need to do this, and their boards have worked fine without this. If you do want to add the cutout, which some datasheets recommend you do, you can add this keep out area and just draw on the inner copper layer, keep out copper poles, click OK, and just make sure under the crystal and under the crystal traces that there's no ground fill. And then you would just attach the grounds via thin traces to the main ground island, right? So in here you can see it's cut out, and then you'd use just really fairly thin traces from ground into the main ground fill. Now, as I said just now, a lot of people didn't have to do this, and their crystals just worked fine. So we won't do it in this video. Okay. So let's have a look. Now we need to do the same thing we did for the 3.3 volt lines for the grounds. So again, click on via, drop it somewhere where there's a ground, change the grid size, and we can pretty much just go mental. Again, close to the ground pads themselves. We'll make sure you're keeping enough clearance from all the traces. Okay. Right, what else do we have? We have these over here. Again, this is a bit boring, but unfortunately necessary. But of course, this is much easier than routing ground and power on a two-layer board. And as we saw, it's really inexpensive to do this in terms of manufacturing. And I just feel like it makes the board look a lot cleaner as well. So, okay, before we do the power section, I almost got carried away there. Let's do these grounds. So, one per pad as a minimum, I'd say. Okay, I'm always just pressing Control D to duplicate. One for this power LED over here. I'm going to put an array here next to the USB connector. Again, just minimize inductance, because this could be a power source as well, right? Make sure. Okay, so now we're pretty much back at the power section. As we did with the 3.3 volts, we want to pretty much scatter this with loads of ground VAs as well. Ideally, tightly packed, and a fair number of them. So that's what I'm doing right now. Of course, you could use greater vias if you require greater current carrying capabilities. But for our purposes here, this is definitely more than enough. This is my tried and tested method. And it works, which is always good. Okay. We're coming close to the end of this via placing mania. Because the V is here, the same net, we can place them fairly close together. You just have to watch the drill to drill distance. That isn't what your manufacturer can't do. Okay, and just a couple of vias from the ground pin out here. Okay, now again, wide traces, let's link them up. So just go through all the vias we just placed. Thick, short traces to link everything up. I'm not sure, did I use 1mm here? I believe I did. Again. Right. Again, we could have done this with kind of ground pause, but it's alright. Okay, now we have all of this stuff. All of these. Did I use 0.5 I used there? Okay, so 0.5. Here again, the whole tombstoning thing. Just be aware of that. Now I could put another via next to the crystals, of course. One thing I would be aware of is that you don't want to put vias on Silkscreen, because that just makes it look really, really rough. Right, you're pretty much drilling a hole into the Silkscreen, and that isn't great. So I don't recommend you do that. Of course, you don't want to limit or hinder the functionality. Okay, here I missed one of the 3.3 volt connections, or vias. Okay, so let's see, everything looking all right. Okay, this one needs to be linked, and this one needs to be linked. Okay, so that's pretty much that. Now, of course, we still have to do this ground thing over here. These ground connections, so a small trace because of limited by this connector. And then we just link all of these up by thick traces. Again, a power pole would be much neater. We of course need to link this up to the internals of this IC as well. Might use a thinner trace actually. Let's actually add another one, a 0.4mm track. See that here? Whoops, selecting it would be good. Okay, so just through here, and I just did that so I can actually get out here with the ground. And as soon as I'm out, I'm just going to drop a via. Okay, so we have this thing here, because it always thinks these are all part of the same net. I'm sure there's a more elegant way of solving that, but for now this is fine. Okay, so I think we are almost done. There's a couple of loose connections here, but that's pretty much the routing, I think, done. So press B again just to refill all the ground pores, and then we can do the first design rules check. Click that, and we can see, run DRC, we can see we have 0 problems, so nothing's too close, nothing's, crossing over or anything, and we have no unconnected items. That's really good. So we can go through the 3D viewer and see, okay, yeah, this looks fairly decent. We've got power traces nice and thick. We've got space and clearance between the parts that need clearance, or the higher frequency signal traces. And we've got vias at pretty much every ground and 3.3 volt point. So that's pretty good. Yeah. So what's left to do now is, of course, you check the schematic again, you check your routing, you check your layout again. We could add 3D components just to make this board look a bit nicer. But instead, let's focus on time on actually making this board a bit more usable, and we have to add Silkscreen to do that. So Silkscreen, we need to add, for example, to tell people what they are actually plugging into. So click on Silk, click on Add Text. Let's change my grid again. This connector up here was an I2C. So I could just put that over here. This connector down here was a UART connector. I mean, it's kind of obvious, but I'd like to put it down somewhere as well. This is just the USB, and then this could be data, do anything, and this is our kind of power connector, right? Power, what else do we have? This is our boot mode switch. So boot mode over here, again, 3D viewer. Just to see, we want to label everything pretty much. That's all I'm doing now. I'm just adding Silkscreen to label stuff, and I'm sure you can do a much nicer job than I'm doing here. For the sake of time, you can either call this SWD or debug. And put it next to the header here. We want to indicate that this is the power LED, or we could say this is a 3.3 volt LED, for example. And we could indicate that this LED down here, of course, is our status LED. All right, so you just want to make sure the user who's ever going to be using this board, you've marked the relevant things. So you've marked the power input, the USB, all what the terminals are doing, that one of them is serial wire debug, and stuff like that, right? Also see, this is currently a socket, but we actually want that to be a header. So that's why the 3D view is useful as well, because I selected the wrong footprint. Now, a way to remedy that is just go back to the schematic, double-click here and change footprint. And I want it to be not a pin socket, but I want it to be a pin header. Pin header and 1.27mm pitch. A pin header, and it's a 2x5. Yeah, so that was my mistake. Vertical SMD. Okay, again, I'm just going to re-export the netlist. Go back to here, and again, update PCB from schematic. So now, unfortunately, that was my mistake. The pin assignments have kind of gone out the window. This is actually what it should be like. So we kind of have to do a tiny bit of rework on the rerouting. Okay, so the N reset line, I'm just going to go over here. Again, once I switch to other layer, I don't like staying there for long. So as soon as I can, I'm going to come up again with a via, and then just route myself to the N reset pin over here. The SWO, we need to connect. SW clock. SWDIO. Okay. Okay, now we just need to do the ground and the 3.3 volts. Okay, well, so this is a lot of the Silkscreen already done. What we're missing now is maybe a logo, which you could put somewhere here. And we could also indicate the polarities of everything, and also the pin 1 locations. And that's something I think you should always do. So to do that, I go to the Silkscreen layer, and I click on this Add Graphic Circle. And then I just go to my pin 1s, and just draw a circle. You might need a smaller grid for this. But it doesn't have to be very large. This is just to indicate, essentially, to the assembly house, make sure this is pin 1, right? So all my ICs, let's see, here's another IC. I will just draw a little circle right next to pin 1 to indicate, yes, this is pin 1. I know KiCad has some internal kind of marking system, but I don't think it's immediately obvious which ones are pin 1 and which things aren't. Doesn't really matter what they look like, just make sure there's a little dot there indicating pin 1. Okay, so I typically just draw an arrow just to indicate for something like a serial wire debug connector, yep, yes, this indeed is pin 1 and I should orient my connector correctly. So you can either do it just by drawing silk lines. If you want the arrow filled in, you can use this Add Graphic Polygon tool over here. Other than that, we also need to annotate the polarities of the diodes, so light emitting diodes and normal diodes. I just use the Silkscreen layer, click on text, and I just put in a little plus. Typically I make it 0.8, 0.8, and not very thick. I don't want this to be too visible, just visible enough that the manufacturer gets it correct. Okay, so we have one diode here, and we have one diode here. Again, you don't want to put the Silkscreen directly on the hole of the via, otherwise you're going to get something that doesn't look very nice. So in this case, I've kind of put it next to it, right? Also, you don't want to make it too confusing. This plus looks like the connector might actually be the plus side here, whereas the plus side of the connector is over there. But that's something we should indicate as well. So next to my connectors, I typically make a much larger sign saying, here, this is actually the positive terminal. Okay, and this will be visible even when the connector is then mounted on top. And then from that, it's fairly clear that the other side must then be the negative terminal. At least one would hope it would be. We also, of course, want the light emitting diodes to have polarity markers. One here and one on this side. Okay, is there anything I've forgotten is the question. Of course, we also have the boot mode switch up here, and it would of course be nice to know as a user which way do I need to push this to make sure I'm actually putting into the mode I want it to, right? So we could just call it boot, or we could just move another one down here and call that run. Because remember, when this thing is low, when this switch is pulled low, we're on run mode. If the switch is pulled high, we're on boot mode. So that way you can quickly see, this is how to set this switch. Okay, so just I would always recommend just be clear on your Silkscreen, as clear as you can be. Another thing I typically do, but I typically do that on the back Silkscreen, is just say what pins are what, right? I might just put a minus sign here. This is ground. I might put a plus sign here. This is 3.3 volts, and the rest, SDA, SCL. But for the sake of time, I'm not going to put that on now. This is just, the majority of this video should be just focused on this STM32 and possibly this buck regulator. As you can see, I've also added some extra Silkscreen that includes a logo, little logo here, and just the name of the board. You can also, of course, put the date of the board when you made it, and that's probably a good idea. But a revision number, I think, as a minimum is what you should do. In the previous video, I told you how to make these Silkscreen logos, but I won't go into too much detail. Essentially, all you need to do is get a graphic you have, preferably black and white, and then all you need to do is use that bitmap to component converter and create a library footprint, import the library, and then it'll appear as a footprint here. To make sure this footprint doesn't disappear, double-click and click Lock Footprint. So anytime you click Update PCB from Schematic, this Silkscreen won't disappear. What we want to do now is actually get this thing ready for manufacturing and assembly, so let's do that. The first thing we need to do is, because we want to hide the order number, JLCPCB typically adds an order number, or we can pay to remove it, but we can also place it underneath a component to hide it completely. The way you do that is go to the F-Silk layer, click on text, and type in JLC 4 times. Make sure it fits, so let's make it a tiny bit smaller. Alright, so we've kind of just hidden it under this component. So in the 3D viewer, we can see this, the number is now hidden, and that's where the actual order number will get printed, instead of getting printed on the middle of your board or somewhere. If we're going to do assembly, we should also add tooling holes as well. Now there's two ways of doing this. Either you add effectively like a mounting hole or a footprint of a certain size, or you can use the edge cuts layer and draw a circle of a certain radius. So we can do that, just click anywhere, edge cuts layer, and we want a radius of a 0.576, I believe. And you want about 2 or 3 of these holes scattered across the board. So that's one way of doing it. I think I've actually made a footprint of the tooling hole. Yeah, so JLCPCB mounting hole, I've just made myself a little footprint, and I'm just going to put 4 of these in convenient locations. Now you can get JLCPCB to do this for you, but, might as well do it ourselves. So just 2 or 3, you could do more, but they don't really need too many of them. Okay. Again, it's probably advisable either to put these in your schematic or to click Lock Footprint on all of them. Right, so lock footprint, and lock footprint. And that's pretty much all we need. We need a couple of these tooling holes, and we need to hide the order number by doing this. And once we've done that, we're pretty much ready to export the files so we can send that off to JLCPCB. Okay, so here's my folder which contains my KiCad project. What I'm going to do is create 2 additional folders. One is called Gerber, and the other is called assembly. So once I've done that, we need to create the Gerber files and all the assembly files. The first thing to do is the Gerber files. So click up here, File, Plot, and then we choose our output directory, which will be Gerber. And yes, I would like to use a relative path. First of all, let's generate the GIL files. Essentially, all these settings are absolutely fine. Click Generate GIL file. All these settings are absolutely fine. And click Plot. Maybe, actually, let's get rid of Generate Gerber job file. It'll ask us if you want to refill the zones. Let's do that. Awesome. Again, you might want to check again that the DRC is okay and so on, but we've already done that before. Okay, so now we've got all the Gerber files. We can go back into the folder, and we'll need to zip these. So I'll just do right-click and add to gerber.rar, and let's just call that a sensible name to Gerber. How about that? Because that's what then we'll upload to JLCPCB. Okay, next thing we need, because for the pick-and-place machines, we need to put the centroids of each of these components. The way we do that is via footprint position file. So click on File, Fabrication Outputs, Footprint Position File. For now, let's just put in the Gerber file. We'll move that in a second. I typically include this as well. All of these are fine, and click Generate Position File. Okay. Now let's move that over to the assembly part. I typically rename it. You don't have to. I will add this in Notepad because there's a couple changes we need to make for JLCPCB to recognize this, because they have some sort of automated system. So change ref to designator, change val to value, package, I believe you should change footprint, pos x change to mid blank x, and pos y to mid blank y, rot to rotation, and side to layer. All of this is on JLCPCB's website as well. After this is just in condensed form. So you have everything here. Yeah, so that's pretty much all good. Now we actually need to go to the schematic again, because we've created the footprint position file and we've created the Gerber files. We need to create a bill of materials now. So let's go back to the schematic, which is here. And we also need to give all of these components essentially part numbers. And this is a bit boring, but you can click up here, click Edit Symbol Fields, and we're going to add a field here. And we're going to call it LCSC blank part blank hashtag or number. And this will create an additional column here. And what we need to do now is essentially go to JLCPCB, click on this link here, click on in-stock parts, and essentially the short link is jlcpcb.com/parts. Now for all the parts we have here, we essentially need to find the LCSC part number. So I will just show you a couple how I do this, and then I'll just skip over it because it's always just repetitive. So if I want to find a 10 microfarad 1206, I go to JCSC, 10 microfarad 1206. It'll load, and you can see I've got one basic part, which is exactly the one I want. 1206, it's 10 microfarads, it's 50 volts. Perfect. So I copy this LCSC part number, put it in there, and so on. So I do that for all the passives, I do that for everything else. So I could do another one. For example, there's STM32. I'll copy the name, paste it in over here. It's a basic part, which is great. Open it up, copy the part number. And that's pretty much all you have to do. So I'll just do that, and then I'll get back to you. So I filled in all the gaps, or the ones that could be filled in the LCSC part number. As you can see, there's still some empty spaces here. And these are things, for example, like the mounting holes. Of course, they're not going to have a part number. But also things, for example, like all these connectors and through-hole components. Unfortunately, JLCPCB doesn't offer that yet. They might do in the future, I hope. But yeah, so all of these through-hole things, we're going to have to solder ourselves. But yeah, but all the kind of S&D parts we found at their library, we can put in the part number. So once you're done with that, click Apply, Save Schematic and Continue, and click OK. Next thing we want to do is actually export the bill of materials. The way we do that is click on BOM, and there's actually someone wrote a KiCad JLCPCB assembly service BOM. I believe if you just Google it, you'll find who did that. Download that, and that'll then export the relevant fields, and we don't have to do any more editing. So I just click on Generate, and then I look back in my folder here. It's put it over here, and I move that into my assembly folder. And the structure of that, we can just have a brief look at. Looks something like this, right? It's just the designators, the footprint, part numbers, and kind of a comment of what the value is. So now we can go ahead with ordering. On the JLCPCB website, you can just click Quote Now. That'll take us to this next site. We want to upload our zipped file of the Gerbers, which is right here. Double click on that. It'll upload and process the Gerber files. And we'll also have another chance to look at the Gerber files using their online Gerber viewer. I'd also recommend, in general with most PCBs, just use the KiCad Gerber viewer up here, just to check and make sure that your ground fills are okay, your copper pores are okay, all the traces look good, the clearances and so on. But you can also do that in the KiCad in the JLCPCB Gerber viewer. It'll import how many layers we have, it'll import the correct dimensions. What we now need to choose is the quantity. There's only one different design, all of this is pretty much fixed. One thing we do want is impedance control. So click on yes here, and this is the stack up we want. This is the one we designed the differential pair for. For assembly, we can only choose green at the moment, and I would urge you to either get lead-free, hot air surface leveling, or this ENIG over here. So let's go with lead-free. And yeah, remove order number is important. Remember, we specified an order number location, so click on specify location. Next thing you need to do is we want SMT assembly. So click on that. We put all the components on the top side for a reason, and this is the reason because, well, we want the top side assembled. Here we go. We want 5 assembled. You can get up to 30 assembled at the moment, I believe. We've added tooling holes ourselves, so click on added by customer. Click confirm, and just wait a tiny bit. Then, once it's saved that, you can click next. Okay, so here we have to upload all our kind of assembly information. That's the bill of materials and the footprint position file. So click add BOM, navigate to the assembly folder, upload the BOM. Same thing for the footprint position file. And then we can just click next. The next step is we actually need to verify our data with what the automated system of JLCPCB has found out. So we compare this left side with this right side to see everything matches up. So make sure 10 microhenry and the footprint is the same as 10 microhenry and the footprint here. And you would go through this list, check left and right, and make sure everything's okay. Now I've already done this for you. Some parts will not be selected, of course. For example, these through-hole parts. Of course, there's nothing in the library we actually chose. But yeah, but check that and then click on next. So here we can actually verify the parts placement to see if everything's kind of in the correct position, if the orientations are correct, and so on. It'll actually also show you the total price. And for me, this is about 56 euros for 5 boards. Of course, it gets cheaper per board the more boards you order, but still about 11-ish euros per board, excluding shipping, is pretty good. Okay, one thing that is left to do is actually correct the parts placement. There is also some tiny bug in the JLCPCB Gerber viewer sometimes where these pads are drawn a bit weird. But you can typically ignore that and the boards come out as you sent them off. But yeah, one thing is we need to correct the orientations. Now you don't have to do this. Essentially JLCPCB will do this for you because we've marked all the pin 1 locations and as well as the anodes and cathodes of the diodes. So, but I typically do it anyway. I guess, clears my conscience. So, we open footprint position files, and we kind of put these two things next to each other. Let's start with U2. U2 is 90 degrees off. Now, the coordinate system they use, essentially, the rotation is positive counterclockwise. So that means we have to rotate U2 backwards counterclockwise by 90 degrees. So you can see on the left here, this is our rotation, so we have to subtract 90 degrees, and it wraps around to 360. So that's 270. So let's have a look at U1 and U3. U1 is 180 degrees off, so that's easy. So that becomes 270. And U3 is the USB thing over here. That's also 180 degrees off. So we can just make that 0. And I believe it's because KiCad and JLCPCB use different standards of rotation. Okay, we also need Q1 to be rotated by 180 degrees. What else do we have? The diodes seem to be correct. Inductor doesn't have an orientation. The diodes, I think, are typically correct. So I think that's all we had to rotate, is these 3 ICs and this component over here. So we can go back, because we've saved this in Notepad, and we can re-upload the data. So we can re-upload the footprint position file, click Next, and then click Next again. And with any luck, everything's correctly rotated, right? Everything's lined up with the pin 1 locations, and everything's looking good. Again, ignore the pads looking like this. That's just, I think, some little bug in their viewer. Once you're happy with that, all that is left to do, after, of course, you've checked everything, is click Save to Cart. You'll have to, of course, solder these kind of through-hole parts yourself, but to be honest, for that price, and yeah, this is pretty cool that this is available these days. With that being said, click Save to Cart. You can choose your shipping option, and that's pretty much it. So I do hope you enjoyed this video. I hope you learned a tiny bit, even though it's a fairly long video. If you haven't subscribed already, please do subscribe and leave a like if you like the video. If you have any questions, please leave them in the comments. Thank you very much for watching, and until next time.